Hello there, and welcome back to Science to Fall Asleep. Tonight, we are going to leave the familiar universe behind. Not because the familiar universe is ordinary. It isn't. Even the sky above you, with its handful of visible stars, is filled with objects so enormous, so ancient, and so powerful that the human mind can barely hold their true scale. But beyond the stars we usually talk about, beyond the planets and galaxies that appear in textbooks, there is another universe. A quieter universe. A stranger universe. A universe filled with things that are exceptionally difficult to find. Some are rare because only a tiny number are known. Some are rare because they exist for only a short moment. Some require such extreme conditions that they almost seem like accidents of nature. And some are rare because they are so faint, so distant, or so hidden that they can remain invisible even when they are physically enormous. Tonight, we will slowly move through that hidden universe. There is no need to keep track of numbers. There will be no rushing from one discovery to another. Instead, imagine that we are floating through space together, moving gently from one extraordinary object to the next. The darkness around us is almost complete. Far away, stars shine like tiny points of warm light. But between those stars are enormous distances. Distances so large that even light, moving at nearly 300,000 kilometers every second, can require thousands, millions, or billions of years to cross them. And somewhere within those distances are the rarest things we know. Perhaps the first thing to understand is that rarity in astronomy is different from rarity here on Earth. On Earth, something can be rare because there are only a few examples. A rare flower may grow in only one valley. A rare mineral may exist in only a handful of places. A rare animal may have a very small population. But the universe is so large that something can be incredibly rare and still exist hundreds or thousands of times. A particular type of star might be found only once in every million stars. That sounds extraordinarily rare. But if a galaxy contains hundreds of billions of stars, there could still be thousands of them hidden within the galaxy. And then there are things so rare that astronomers may know of only a few examples. These are the objects that make astronomers pause. They are the cosmic exceptions, the strange survivors, the unusual combinations, the events that nature seems to produce only under very specific circumstances. And perhaps one of the most beautiful examples begins with something that looks deceptively ordinary. A star. A star can spend millions or billions of years appearing almost unchanged. From a great distance, it may seem like a simple point of light. But inside that point of light, gravity and nuclear physics are constantly fighting one another. Gravity tries to crush the star inward. Energy produced in the star's interior pushes outward. For most of its life, these forces balance. The star remains stable. It shines, it ages, and eventually, depending on its mass, it reaches a point where that balance can no longer continue. For massive stars, the ending can be spectacular. The core becomes increasingly dense. Nuclear reactions change. Different elements begin to form. The star moves through increasingly advanced stages of stellar evolution. Eventually, the core can become dominated by iron, and iron represents a boundary. Fusing iron does not provide the same kind of energy that earlier nuclear fusion reactions provide. The star can no longer support itself in the same way. Gravity suddenly becomes overwhelmingly important. The core collapses. In a fraction of a second, enormous amounts of matter can fall inward. The outer layers respond violently. A shock wave moves through the star, and the star explodes. A supernova. For a short time, A single exploding star can become extraordinarily bright. But even a supernova is not necessarily the rarest thing associated with stellar death. What remains afterward can be much stranger. If the collapsing core is massive enough, the matter can be compressed into a neutron star. Imagine taking more mass than the Sun and compressing it into something roughly the size of a city. The result is one of the densest objects in the observable universe, a neutron star. Its surface is unimaginably solid compared with anything we encounter naturally. Its gravity is enormous. A person standing on it would experience forces so extreme that the concept of standing would almost cease to make sense. And yet the object can remain only a few tens of kilometers across. This is one of the first great cosmic paradoxes. A star can die and become smaller than many cities. Its mass remains enormous. Its density becomes extraordinary. And its existence is governed by physics that does not resemble everyday experience. Inside a neutron star, matter is compressed so strongly that atoms can no longer exist in their familiar form. Electrons and protons can combine under extreme pressure. Neutrons become dominant. The star becomes, in a sense, a gigantic nuclear object. But even neutron stars are not all alike. Some rotate extraordinarily rapidly. Others possess magnetic fields so strong that they become magnetars. Some emit beams of radiation that sweep across space. When those beams happen to point toward Earth, we may detect regular pulses. These objects are pulsars. Imagine a lighthouse in an ocean. The lighthouse rotates. Its beam sweeps across the water. A distant observer sees flashes at regular intervals. A pulsar works in a similar conceptual way. Its radiation beams sweep through space as the neutron star rotates. If Earth happens to lie in the path of the beam, we detect pulses. Some pulsars rotate many times per second. A few rotate hundreds of times each second. The object is incredibly compact, yet it can spin with extraordinary speed. The physics is almost difficult to imagine. A star that once resembled something like the Sun has collapsed into a city-sized sphere. It is rotating hundreds of times each second. Its magnetic field is enormous, and its radiation is sweeping through space like a cosmic lighthouse. But even among pulsars, there are unusual examples. Some pulsars are part of binary systems. They orbit another star. Sometimes the companion transfers matter onto the neutron star. This can dramatically alter the system. The neutron star may gain material. Its rotation can accelerate. Astronomers sometimes call these objects recycled pulsars. They are stars that have effectively been spun up again. A dead stellar remnant receives new material from a companion and begins rotating faster. The universe has created a kind of stellar resurrection, not a living star returning to life, but an ancient compact remnant receiving energy and matter from its surroundings. And then there are millisecond pulsars. They rotate so rapidly that their periods are measured in milliseconds. Imagine something with more mass than the Sun rotating several hundred times every second. The surface is moving incredibly fast, yet the star remains gravitationally bound. Its compactness allows it to withstand this rotation. Some of these objects are remarkably stable. Their pulses can arrive with astonishing regularity. In some cases, pulsars can be used almost like cosmic clocks. Their timing can be measured with incredible precision. And this leads to another remarkable possibility. If a pulsar has a planet, the planet can slightly influence the pulsar's motion. Those tiny changes can alter the timing of the pulses. Astronomers can sometimes infer the existence of planets around pulsars by measuring these variations. The first confirmed planets discovered outside our solar system were found around a pulsar. Think about how strange that planetary system must be. A world orbiting the remains of a dead star. Its sky would be illuminated not by a normal yellow star like our sun, but by the radiation and periodic pulses of a neutron star. The original star may have exploded. Its planets may have been destroyed, altered, or destabilized. Yet planets can somehow remain or later form from the material around the remnant. It is one of the strangest settings imaginable for a planetary system. And then, among neutron stars, there is a category even more extreme. Magnetars. A magnetar is a neutron star with an extraordinarily powerful magnetic field. The field can be trillions of times stronger than Earth's magnetic field. Its effects are difficult to visualize. A magnetar's magnetic field can influence the behavior of matter and radiation over large distances. And occasionally, the magnetic field undergoes sudden changes. The crust of the star can fracture. The magnetic field can rearrange. Energy can be released in an enormous burst, a giant flare. For a brief moment, a magnetar can produce an astonishing amount of high-energy radiation. The event may last only fractions of a second, and then the universe becomes quiet again. This is an important theme in our journey. Some of the rarest things in space are not permanent objects. They are moments. A brief flash, a sudden explosion, a collision, a flare, a pulse. A transient event that may occur once and never repeat in exactly the same way. Imagine watching the night sky for your entire life. The stars appear stable. But if you could somehow observe the universe continuously across millions of years, you would see it changing constantly. Stars would explode. Galaxies would merge. Black holes would consume matter. New stars would be born. Neutron stars would collide. The universe is not static. It only appears static because human lives are incredibly short compared with cosmic timescales. Now let us travel farther. Imagine two neutron stars. They are already strange objects individually. Now imagine two of them orbiting one another. Their gravitational fields interact. They slowly spiral together. The system loses energy through gravitational waves. Space itself begins carrying away energy from the orbit. The stars move closer. The orbital period becomes shorter. Their speed increases. Eventually, the final moments arrive. The two neutron stars collide. This is one of the rarest and most dramatic events we can observe. The collision sends gravitational waves through the fabric of space-time. It can produce an intense burst of radiation, and it can create extremely heavy elements. Gold, platinum, and other elements that require extreme environments to form. For a long time, astronomers wondered where many of these heavy elements came from. The collision of neutron stars provided an important answer. The universe has enormous factories for rare elements. But these factories are not ordinary stars. They are stellar remnants. Dead stars. Objects created by destruction. Two compact remnants can collide, and from their violent meeting, new matter can emerge. That means something beautiful and strange. Some of the gold on Earth may have originated in catastrophic events involving neutron stars long before the Sun and Earth existed. Imagine that. A piece of jewelry resting quietly on a table could contain atoms that were once part of an ancient cosmic collision. Those atoms may have been created billions of years ago in a violent event far beyond the Milky Way. They were scattered into space. They mixed with gas. That gas eventually became part of a new generation of stars. Around one of those stars, planets formed. One planet became Earth, and much later, humans discovered the material and gave it value. The universe does not label anything as precious. It simply creates elements. We are the ones who decide what they mean. Now let us move toward another rare remnant, a white dwarf. A white dwarf is the leftover core of a star that was once similar in broad terms to the Sun. When such a star reaches the end of its normal life, it can shed its outer layers. The remaining core becomes a white dwarf. It no longer performs ordinary hydrogen fusion like the Sun. Instead, it slowly cools. The object can be roughly Earth-sized while containing a substantial fraction of the Sun's mass. That means its density is enormous. A small amount of white dwarf material would weigh an extraordinary amount under Earth's gravity. But perhaps even more fascinating are white dwarfs that live in binary systems. A white dwarf may orbit a companion star. Its gravity can pull material from that companion. Gas flows toward the white dwarf. It forms a disk. The material spirals inward, and eventually, enough hydrogen can accumulate on the surface. Pressure and temperature rise. Then nuclear reactions ignite suddenly. The surface erupts. A nova appears. The white dwarf survives. The event fades, and the process may happen again. Some systems can produce multiple eruptions. These recurrent novae are particularly rare. Imagine observing the same star brighten dramatically during your lifetime, then fade. Years pass, and it happens again. The universe has repeated the explosion, not because the star is being destroyed, but because the system is accumulating fuel again. It is almost like a cosmic heartbeat, slowly gathering, suddenly releasing, returning to quiet, gathering again, and releasing again. But if the conditions become extreme enough, a white dwarf can face a very different ending. If it gains enough mass, the star can become unstable. A thermonuclear explosion can consume much of the white dwarf. A Type Ia supernova can occur. Unlike a massive star supernova, this kind of explosion can come from a compact stellar remnant. The brightness of these explosions makes them particularly useful to astronomers. They can be seen across enormous distances, and because their intrinsic brightness follows relatively predictable patterns, they have been used as cosmic distance indicators. Astronomers can observe the apparent brightness and estimate how far away the explosion occurred. In this way, a violent stellar death becomes a measuring tool. The universe destroys a star. Humanity uses the light from that destruction to measure the universe itself. That is another recurring pattern. Nature creates something extreme, and humans learn to turn that extremity into information. Now, not every rare object has to be violent. Some are simply ancient. Consider the oldest stars. The universe began in a hot, dense state approximately 13.8 billion years ago. The earliest generations of stars formed from material that was overwhelmingly hydrogen and helium. There were very few heavier elements. Those heavier elements had not yet been created in large quantities by stars. The first stars changed that. They forged new elements. Some exploded. Their material entered the surrounding gas. Later stars formed from chemically enriched material. Over time, the universe became increasingly rich in elements beyond hydrogen and helium. That means the chemical composition of a star can tell us approximately when and where it formed. A star with extremely low amounts of heavy elements may have formed from relatively primitive gas. Some such stars may be more than 12 billion years old. They have survived almost the entire history of the universe. Think about what that means. When the star formed, Earth did not exist. The Sun did not exist. The Milky Way had not yet developed into its modern structure. There were no humans, no dinosaurs, no oceans on Earth, no Earth at all. The star was already shining. For billions of years it remained in the universe. Stars around it were born and died. Galaxies merged. Black holes grew. Planets appeared. Life evolved somewhere. And the ancient star continued shining. These stars are among the greatest archaeological treasures in astronomy. They preserve clues about the early universe. Their light is like a message from a time almost beyond imagination. Some of the oldest known stars are not only old, but chemically unusual. They may contain traces of elements created by the first generations of massive stars. By studying them, astronomers can reconstruct pieces of cosmic history. It is like finding an ancient artifact that has never been buried. The artifact is still alive, still glowing, still moving through space. But its chemistry remembers an earlier age. Now imagine something even stranger. A star that appears to be almost entirely made of hydrogen and helium, with incredibly little of the heavier elements astronomers expect. Such stars are exceptionally valuable. They may have formed early in cosmic history, and the search for the most chemically primitive stars continues. Perhaps somewhere in the Milky Way, an even more ancient survivor is waiting. A star formed from material barely changed since the earliest generations of cosmic history. Finding it would be like opening another page of the universe's childhood. The universe itself is an enormous archive. Every star contains information. Every spectrum contains clues. Every explosion leaves chemical fingerprints. Every galaxy carries evidence of its past, and the rarest objects can sometimes preserve the clearest memories. Now let us move away from stars altogether. Imagine a galaxy that is enormous but strangely faint. You might expect a huge galaxy to be bright. After all, if it contains many stars, shouldn't it shine strongly? Not necessarily. Some galaxies spread their stars over enormous areas. Their light becomes extremely diffuse. They are called low-surface brightness galaxies. From a distance, they can almost disappear into the background sky. Imagine taking a handful of glowing dust and spreading it across an entire football field. The total amount of dust might be large, but the glow in any single location would be faint. That is roughly the challenge astronomers face with these galaxies. Their total amount of matter can be substantial, yet their surface brightness is low. Some are dominated by dark matter. Some contain unusual amounts of gas. Others may have evolved differently from more familiar galaxies. And because they are difficult to detect, we may still be missing many of them. The universe could contain enormous numbers of faint galaxies that remain below the sensitivity of many surveys. This is one reason astronomy keeps changing. Every improvement in telescope technology reveals objects that were previously invisible. A galaxy that did not appear in an older survey may suddenly become obvious in a deeper observation. A faint star may emerge from the background. A distant transient may appear. A previously unknown population may be discovered. The universe is not necessarily changing. Our ability to see it is changing. And every time our vision improves, the definition of rare can change. Something once thought to be almost unique may turn out to be one member of a larger population. Something else may suddenly become the new rarity. That is why astronomy remains so open-ended. The catalog is never finished. Now imagine a galaxy that contains a supermassive black hole at its center. Most large galaxies are believed to host massive black holes in their central regions. But occasionally, a black hole becomes exceptionally active. Material falls inward. An accretion disk forms. The gas heats to enormous temperatures. It can emit intense radiation. The galaxy becomes an active galactic nucleus. Some active galaxies can produce jets. Powerful streams of particles can travel outward from the central region at speeds approaching that of light. These jets can extend far beyond the galaxy itself. They can stretch across hundreds of thousands or even millions of light years. Think about that scale. A black hole in the center of a galaxy, itself invisible, can influence matter across a region vastly larger than the galaxy's central stellar environment. Some jets are among the largest individual structures associated with galaxies, and yet the engine driving them is extraordinarily compact. A region close to a black hole can power a structure that reaches far into intergalactic space. This is another cosmic paradox. Tiny source, enormous consequence. A black hole can be physically compact while influencing a region unimaginably large. And then there are black holes that are unusually quiet. A supermassive black hole can exist in the center of a galaxy without currently consuming large amounts of matter. It becomes difficult to detect directly. Astronomers may infer its existence through the motion of nearby stars or gas. The black hole can sit quietly for millions of years. Then a cloud of gas approaches, or a star wanders too close, or some other disturbance changes the environment. Suddenly, material begins falling inward. The black hole becomes active. Radiation increases. The surrounding region brightens. A previously quiet galaxy changes. This is the nature of cosmic rarity. The event may have been possible for billions of years, but the timing is unpredictable, and we happen to live during the tiny interval when the light reaches our telescopes. Now let us imagine one of the most dramatic rare events involving a black hole. A star approaches too closely. At first, nothing seems unusual. The star is simply moving through its galaxy. But as it enters the black hole's gravitational environment, the difference in gravitational force across the star becomes enormous. The side facing the black hole experiences a stronger pull than the far side. The star stretches. The effect becomes stronger. The star begins to resemble a long stream. Eventually, it can be torn apart. Some material escapes. Some becomes gravitationally bound. A disk can form. Radiation increases. The distant galaxy brightens. Astronomers call this a tidal disruption event. These events are rare because stars need to pass through a relatively small region around the black hole for the tidal forces to become destructive. Most stars orbiting the black hole never approach closely enough. They continue their paths. One star, however, may make the wrong turn, and that single trajectory can transform the appearance of an entire galactic nucleus. For a while, the universe produces a beacon. Then it fades. The star is gone. The black hole remains. And the galaxy becomes quiet again. Now let us leave that galaxy behind. Farther, much farther. Eventually, individual galaxies become tiny points. Then even those points disappear. What remains is an enormous cosmic network. Matter is not spread evenly. Gravity has organized the universe into a web. Filaments of galaxies connect enormous clusters. Walls of matter stretch across vast distances. Between them lie huge, underdense regions called cosmic voids. A cosmic void can extend across hundreds of millions of light years. Within it, galaxies are comparatively scarce. If you could travel through one, you might pass enormous distances without encountering a dense galaxy cluster. The darkness would feel almost complete. Yet the void would not be truly empty. There would still be some matter. Diffuse gas, dark matter, perhaps occasional galaxies. But compared with the surrounding cosmic web, it would be extraordinarily sparse. The strange thing about voids is that they are defined by absence. Their identity comes from what is missing. That makes them a fascinating example of how structure can emerge from emptiness. Imagine drawing a map of a city. You might define neighborhoods by buildings. But in the cosmic web, some of the largest regions are defined by the lack of buildings. The universe contains enormous spaces where matter simply did not gather as strongly. And those spaces have evolved over billions of years. Early in cosmic history, the universe was much smoother. Tiny fluctuations existed in the density of matter. Over time, gravity amplified them. Dense regions attracted more matter. Less dense regions became emptier. The cosmic web grew. So the enormous structures we see today are the descendants of tiny variations from the universe's early history. A tiny difference, billions of years, an enormous result. This is one of the deepest patterns in cosmology. The present universe contains memories of its beginning. The distribution of galaxies is not random. It carries information about the early universe. And perhaps one of the rarest things we can observe is not a physical object at all. It is a moment when light from the early universe reaches us. The cosmic microwave background is ancient radiation released when the universe became transparent to light, roughly 380,000 years after the Big Bang. That radiation has traveled for more than 13 billion years. Today, it fills the universe. It comes from every direction. It is incredibly faint, but it is one of the most important observations in modern cosmology. It gives us a glimpse of the universe when it was extremely young, before stars, before galaxies, before planets, before Earth, before everything familiar. Imagine receiving a signal from a time when the universe was only a tiny fraction of its present age. That signal has been traveling ever since. It passed through expanding space. The wavelength stretched. The radiation cooled. And eventually, it arrived at detectors built by humans on a small planet. Ancient light. Still here. Still carrying information. Still telling us what the universe looked like in its infancy. There are also rare fluctuations within that ancient radiation. Tiny variations in temperature, tiny differences in density. They are incredibly small, but they became the seeds from which later cosmic structures grew. The galaxies, clusters, filaments, and voids. The universe we see today is, in a sense, an enormous expansion of those tiny, early irregularities. A small fluctuation became a galaxy. A galaxy became part of a cluster. Clusters became part of the cosmic web. And billions of years later, we are sitting here talking about the result. Now, as we drift deeper into the darkness, consider another rarity. A gravitational lens. When massive objects sit between us and a distant source of light, their gravity can bend the path of that light. A galaxy cluster can act like a gigantic cosmic lens. The background galaxy may appear magnified. Its light can stretch into arcs. Sometimes multiple images of the same distant object can appear. The effect is a natural telescope created by gravity. Astronomers use gravitational lenses to study objects that would otherwise be too faint or distant to observe clearly. The universe can therefore magnify itself. A massive foreground object bends light from something behind it. The result is an accidental alignment. And because the alignment must be favorable, strong gravitational lensing configurations can be rare. But when they occur, they are enormously useful. They can reveal distant galaxies from the early universe. They can help map dark matter. They can even allow astronomers to study structures that would otherwise be hidden. Imagine a distant galaxy. Its light begins traveling toward Earth. Billions of years pass. Along the way, the light encounters a massive cluster of galaxies. The cluster's gravity bends the path. The light changes direction. Eventually, it arrives here. We observe an image that has been distorted by gravity. The galaxy appears stretched. Its shape is changed. But hidden within that distortion is information. The universe itself has acted like a lens. And once again, something that seems like an obstacle becomes a tool. Now let us move towards something much smaller. A particle. One of the rarest particles to reach Earth can come from enormous cosmic distances. Ultra-high energy cosmic rays are among the most energetic particles ever observed. Their exact origins remain an active area of research. They may be produced by extreme astrophysical accelerators, perhaps active galaxies, perhaps powerful shocks, perhaps other environments we have not yet fully understood. The most energetic examples are extremely rare. A detector can wait for long periods before recording an event. When one arrives, it strikes the atmosphere. It collides with molecules. A cascade of secondary particles develops. That cascade can spread through the atmosphere. Ground-based observatories can detect the resulting shower. The original particle may have been traveling for millions of years. The atmospheric shower may last only a fraction of a second. A cosmic journey that lasts longer than human civilization ends in an instant. That is another quiet wonder. The universe is full of things that take billions of years to happen and only moments to observe. Now imagine the opposite. An object that lives for billions of years but changes so slowly that its evolution is almost impossible to see. White dwarfs are examples. They cool gradually. Over unimaginably long periods, their temperature decreases. In theory, after enough time, a white dwarf could become a cold, dark object known as a black dwarf. But the universe is not old enough for black dwarfs to have formed naturally. This makes black dwarfs a fascinating example of something that is theoretically expected but not currently present. The universe has not had enough time. Stars have not been cooling for long enough. The cosmos is still too young. Someday, unimaginably far in the future, the universe could contain such objects. But today, they remain hypothetical. This gives us a strange category of rarity. Something can be rare because it does not yet exist. The laws of physics may allow it. The universe simply has not had enough time to create it. And that reminds us that the universe has a future as well as a past. We often think of astronomy as looking backward. Light from distant galaxies shows us the past. Ancient stars reveal ancient history. But physics also allows us to imagine what the universe might become. Stars will eventually stop forming. Galaxies will evolve. Black holes may dominate the distant future. White dwarfs will cool. The universe will gradually become darker. The spectacular universe of today may eventually become a much quieter place. But tonight, we are still living in an active cosmic era. Stars are being born. Stars are dying. Galaxies are colliding. Black holes are feeding. Planets are forming. And rare events are occurring everywhere. We simply see only a tiny fraction. Now let your imagination return to the Milky Way. Somewhere within our galaxy is an enormous population of stars. Most are ordinary. Some are unusual. A very small number are extraordinary. Among them are stars that have consumed material from companions, stars that have merged, stars that have been stripped of their outer layers, stars that have unusual chemical compositions, stars that rotate at extraordinary speeds, stars that pulse, stars that erupt, stars that are dying, and stars that are already dead but remain as compact remnants. The Milky Way is therefore not just a collection of stars. It is a graveyard, a nursery, a laboratory, a museum, a chemical factory, and an enormous cosmic archive. Every region contains stories. Some stories are bright enough for us to see. Others remain hidden. And perhaps some of the rarest things are objects we have not yet learned how to recognize. Astronomy has repeatedly shown us this. Before pulsars were discovered, nobody knew that rapidly rotating neutron stars could produce such regular radio pulses. Before quasars were understood, their immense brightness seemed almost impossible. Before gravitational waves were directly detected, ripples in space-time were theoretical predictions. Before exoplanets became common discoveries, planets around other stars were unknown. The universe repeatedly surprises us by producing things that were not obvious from our expectations. So the rarest thing tonight may not be an object. It may be a discovery waiting to happen. Somewhere beyond our current telescopes, something exists that does not fit our categories. Perhaps it is a new type of star. Perhaps a new type of planetary system. Perhaps a strange interaction involving dark matter. Perhaps an unusual black hole. Perhaps a phenomenon that lasts only seconds but releases enough energy to illuminate an entire galaxy. The universe is under no obligation to be familiar. It only has to obey its laws. And sometimes those laws create possibilities far stranger than anything humans would have imagined. As we continue this journey, we will move deeper into those possibilities. We will encounter stars that behave in ways that seem impossible. Worlds that exist in environments unlike anything in our solar system. Black holes surrounded by extraordinary structures. Galaxies so faint that they nearly disappear. Explosions that last only moments. Particles carrying unimaginable energies. Ancient objects that formed when the universe was young. And phenomena that remain mysterious even after decades of observation. For now, though, let yourself float quietly in the darkness. The stars are far away. The galaxies are farther still. And the rare objects we have encountered are scattered across an almost endless universe. A magnetar turns silently. A pulsar sends another pulse through space. A white dwarf cools. A distant galaxy glows faintly. A black hole waits. A neutron-star travels through darkness. A cosmic ray crosses an enormous distance. An ancient photon continues its journey. And somewhere, two compact stars may be slowly spiraling toward one another. Their final collision may happen millions of years from now. Or perhaps it happened long ago. The light simply has not reached us yet. Space is not only distance. It is time. Every time you look at a distant object, you are looking into history. The farther away the object is, the farther back in time you see. So when we look toward the deepest reaches of space, we are not simply looking outward. We are looking backward. We are seeing ancient light, ancient stars, ancient galaxies, ancient explosions, and ancient events whose participants may no longer exist. The universe is constantly sending us memories. We only need to know how to read them. And tonight, slowly, peacefully, we are learning to read a few of them. There is no need to remember every name. No need to memorize every detail. Let the ideas simply drift through your mind. A tiny particle traveling for millions of years. A dead star rotating hundreds of times every second. A magnetic field stronger than anything found naturally on Earth. Two neutron stars colliding. Gold forged in cosmic violence. An ancient star surviving almost the entire age of the universe. A galaxy hiding in plain sight because its light is spread too thinly. A black hole quietly waiting at the center of a galaxy. A star wandering too close and being torn apart. A void hundreds of millions of light years wide. Ancient radiation arriving from the infancy of the universe. Light bending around gravity. and countless other rarities waiting beyond the horizon. The universe is enormous, but it is also patient. It has time, billions of years, trillions of years, far beyond the span of any human life. And perhaps that is why it feels so peaceful to imagine. Nothing needs to happen quickly. Stars can take millions of years to form. Galaxies can take billions of years to evolve. A photon can cross space for billions of years before reaching a telescope. The universe does not hurry. So tonight, you do not need to hurry either. Let your breathing become slow. Let your thoughts become quieter. Imagine the Milky Way rotating slowly somewhere far away. Imagine the stars moving through their enormous orbits. Imagine the darkness between them. And imagine that within that darkness, the rarest things in space continue their silent lives. Some are bright. Some are invisible. Some are ancient. Some are temporary. Some are violent. Some are peaceful. And some may exist only once in an enormous region of space. We have only begun our journey. There are still many more cosmic rarities waiting ahead. And as we move into the next part, we will go deeper into the strange lives of stars, the unusual objects created when stars interact, and the extraordinary events that can transform one cosmic object into another. For now, simply rest. The universe is still moving. The stars are still shining. And somewhere far beyond the darkness you can imagine, another rare event is unfolding. Quietly, slowly, millions of light years away, and its light has only just begun its journey toward us. The journey continues quietly. Somewhere in the darkness, a star is changing. From Earth, it may appear completely still, a tiny point of light. Perhaps it has been shining for millions of years, perhaps billions. But inside that distant point, gravity is slowly reshaping everything. Stars are not permanent. They only appear permanent because their lives are so much longer than ours. A human life is measured in decades. A civilization may last centuries or millennia. A star can live for millions, billions, or even trillions of years depending on its mass and composition. So when we look at a star tonight, we are seeing one moment in an enormous story. And some of the rarest objects in the universe are stars caught in unusual moments of that story. One of the most intriguing examples is a star that appears to be losing its identity. A massive star can enter a phase where its outer layers are stripped away. Sometimes this happens because of powerful stellar winds. Sometimes a companion star pulls material away. Sometimes the star has already lost much of its envelope during earlier stages of evolution. What remains can be extraordinarily hot. These stripped stars can expose deeper layers that would normally remain hidden beneath the outer atmosphere. They can become compact, luminous, and chemically unusual. Among the most extreme are Wolf-Rayet stars. They are massive stars with powerful winds that can carry enormous quantities of material away from their surfaces. Their outer layers are being removed at astonishing rates. The star is almost revealing its interior to the universe. These stars are rare. They are massive. They are hot. And they live relatively short lives compared with stars like the Sun. A Wolf-Rayet star may have begun its life surrounded by a thick envelope of hydrogen. Over time, stellar winds or interactions with another star strip that material away. The deeper layers become exposed. The star becomes extraordinarily hot and luminous. Its atmosphere can be dominated by helium, carbon, oxygen, or other products of advanced stellar evolution. Imagine a giant star slowly peeling away its outer layers, not in a single dramatic explosion, but through powerful winds flowing continuously into space. The star loses material. That material expands outward. It forms an enormous circumstellar environment. Eventually, some of that material may contribute to the formation of new stars and planets. Even before the star dies, it is already returning its material to the galaxy, and its final death can be spectacular. Some Wolf-Rayet stars are thought to be associated with certain types of core collapse supernovae. Others may be connected with gamma-ray bursts under particular circumstances. These are among the most energetic explosions in the universe. A star that began life as a massive ball of gas can end its existence as an event capable of producing radiation visible across cosmological distances. And yet the star's story is not simply destruction. It is transformation. The star creates elements. The star loses elements. The star enriches its environment. Then the star disappears. Its remains become something else. The universe is constantly recycling stellar matter, and the rarer the star, the more unusual the material it may contribute to its surroundings. Now imagine a different kind of unusual star, a star that seems to be rotating so quickly that it is almost tearing itself apart. Stars rotate. The sun rotates once in roughly a month, although different parts of its surface rotate at different rates. But some stars spin much faster. When a star rotates rapidly, centrifugal effects can distort its shape. Instead of being nearly spherical, the star can become flattened at the poles and wider around its equator. In extreme cases, the star can approach its critical rotation rate. At that point, material near the equator becomes much less tightly bound. Gas can be thrown outward. The star may form a disk of material around itself. These stars are examples of rapidly rotating stars associated with circumstellar disks. Their spectra reveal unusual emission features created by material surrounding the star. Imagine a blue-white star rotating so rapidly that it creates a flattened disk of gas around its equator. The star itself is shining intensely. The disk is made of material that has been pushed away from the surface. From a distance, the system can look different from an ordinary star. The disk can glow. It can produce distinctive spectral signatures. And because the disk can change over time, astronomers can watch the stellar system evolve. Some of these stars may have complicated histories involving binary interactions. A companion can transfer mass. The receiving star gains angular momentum. Its rotation speeds up. The star becomes a rapid spinner. Again, a companion can change the fate of a star. Binary systems are everywhere. Two stars orbiting one another can exchange matter. They can influence one another's rotation. They can alter one another's chemical composition. And eventually, they may merge. Some of the strangest stars may therefore be the products of stellar relationships. A star that appears unusual today may be the result of events that happened millions of years ago. Its current appearance may be a fossil record of an ancient interaction. This makes binary stars especially fascinating. When we look at a star, we may think we are looking at one object, but perhaps we are looking at the aftermath of two objects. Or perhaps two stars are still orbiting each other, quietly shaping one another's futures. And sometimes, the interaction becomes dramatic. Imagine two stars so close that one begins transferring material onto the other. Gas leaves one star. It flows toward the companion. It may form a disk. The receiving star becomes brighter. The donor star becomes stripped. Over time, the system changes completely. Eventually, one star may become a compact remnant. The other may continue evolving. The relationship between the two determines their destinies. Some of the most important objects in astrophysics are therefore not isolated stars. They are systems, pairs, triples, sometimes even larger groups. The universe rarely cares about the boundaries we draw around individual objects. Gravity connects them. Matter moves between them. Their histories become intertwined. And occasionally, two stars can merge into one. Stellar mergers are rare, but when they occur, they can produce remarkable temporary objects. The resulting star may become brighter. It may rotate rapidly. Its chemical composition can be unusual. Its surface can be covered with material that came from both original stars. In some cases, a merger can produce a luminous transient event. One famous class of event is known as a luminous red nova. It occurs when two stars merge. The system can brighten dramatically. Then it slowly evolves into a cooler, redder object. The event is far less common than ordinary stellar variability. It is the visible signature of two stars becoming one. Imagine watching two suns orbiting each other. Their distance gradually decreases. Tidal forces distort them. They exchange material. The orbit tightens. Eventually, their outer envelopes interact. The two stars begin to merge. Gas is expelled. Energy is released. The system brightens. For a while, the sky in that distant region changes dramatically. Then the light fades. The two stars are no longer two. They have become one. The universe has combined them, and the resulting object carries the memory of both. There are few events more poetic than that. Two separate stars, two separate histories, two separate lives, and then one final shared event, a merger. Now, among stellar systems, there are some where one member is almost impossible to see. A black hole can orbit a normal star. The companion shines. The black hole does not. But the black hole's presence can be inferred from the motion of its visible companion. The star moves in an orbit. Something invisible is pulling on it. By measuring the star's motion, astronomers can estimate the mass of the unseen object. If the mass is too large to be a normal star and no light is coming from it, a black hole becomes a strong possibility. These systems are rare and extremely valuable. They allow astronomers to study black holes that are not actively feeding. A quiet black hole, a hidden black hole, a gravitational shadow revealed by the motion of a star. Imagine a star traveling through space. To your eyes, there is only one visible object, but the star is not alone. It is orbiting something invisible. Every orbit is a clue. Every change in velocity is evidence. The black hole is silent. It emits no ordinary light, yet gravity reveals it. This is one of the most powerful ideas in astronomy. We do not always need to see an object. Sometimes we can see what it does. The universe reveals invisible things through their effects. Dark matter, black holes, planets around distant stars, all can be detected through influence rather than direct visibility. Now imagine a black hole that is not quiet. Suppose its companion star is close enough for the black hole to pull material away. Gas streams from the star. It spirals toward the black hole. As the gas falls inward, it forms a rapidly rotating accretion disk. Friction and gravitational energy heat the disk. The material can become extremely hot. The system begins shining in X-rays. From Earth, we may see a powerful source of high-energy radiation. The black hole itself remains invisible, but the material around it becomes extraordinarily bright. This creates a strange contrast. The object generating the gravitational field cannot be seen directly. The material falling toward it can become one of the brightest things in the system. The darkness makes the light. The black hole consumes. The accretion disk glows. And eventually, some of the energy may emerge through powerful jets. Jets are among the most spectacular structures associated with accreting compact objects. Particles can be accelerated and directed along the system's magnetic field. They travel outward. Some reach enormous distances. The black hole is tiny compared with the scale of the jet. A compact engine powers a cosmic-scale structure. Now imagine the same basic idea on a much larger scale. A supermassive black hole at the center of a galaxy begins feeding intensely. The galaxy's central region becomes luminous. The object may be classified as a quasar. Quasars are among the brightest persistent sources in the universe. Their energy comes from material falling towards supermassive black holes. Some can outshine the combined light of the billions of stars in their host galaxies. This is one of the most remarkable examples of gravitational energy conversion. Matter falls inward. Gravitational potential energy becomes heat and radiation. The result can be visible across billions of light years. And some quasars are extremely distant. Their light began its journey when the universe was much younger. When we observe them, we are looking at ancient cosmic history. Imagine a quasar that existed billions of years ago. The galaxy around it may have looked nothing like the Milky Way today. The black hole may have been growing rapidly. Gas was falling inward. Jets were shooting outward. Radiation was crossing intergalactic space. And eventually, after billions of years, that ancient light reached Earth. We see it today, a point of light in a telescope. But behind that point is an entire galaxy and an enormous black hole. This is why astronomy can be deceptive. The sky looks flat. A tiny dot may represent an enormous structure. A faint point may be billions of light years away. A bright object may have existed when Earth was young. The apparent size of something in the sky tells us almost nothing about its actual size. Now let us consider another rarity. A quasar that produces a powerful relativistic jet pointed almost directly toward Earth. Such objects can appear especially bright because of relativistic effects. The jet's emission can be amplified in our direction. These objects are known as blazars. Their brightness can change dramatically. Sometimes they flare. Sometimes they fade. Their light can vary over short timescales. The engine remains far away, but its jet is aimed almost toward us. It is like looking directly into a cosmic beam. And because the jet is moving at relativistic speeds, the observed behavior can be unusual. The brightness can change rapidly. The spectrum can be energetic. The object can become a powerful source of high-energy radiation. Blazars are rare partly because the jet needs to be oriented favorably. The universe contains many active black holes, but only a subset have jets pointed nearly toward Earth. Geometry creates rarity. This idea appears repeatedly throughout astronomy. An object may not be intrinsically unique. The alignment needed to observe it may be rare. A planet may transit its star only if its orbit is aligned with our line of sight. A gravitational lens may be visible only under a particular alignment. A pulsar may be detectable only when its beam sweeps across Earth. A jet may appear especially bright when pointed toward us. The universe can contain countless events that we simply do not see because we are looking from the wrong direction. Now imagine a star that suddenly changes brightness because something passes in front of it. A planet, a small companion, a brown dwarf, or perhaps a compact object. The event is called a transit when a planet crosses the face of its star from our viewpoint. The star dims slightly. For a large planet, the change can be detectable. The brightness returns to normal. If the event repeats at regular intervals, astronomers can infer the planet's orbital period. This simple effect has revolutionized astronomy. We have discovered thousands of exoplanets through transits. But some transits are rare because the geometry is so precise. A planet may orbit its star perfectly well, yet from Earth, we may never see it cross the star. The orbital plane simply does not line up correctly. Another observer located somewhere else in the galaxy might see the transit clearly. This means the universe contains planets that are invisible to us through certain methods simply because of geometry. And sometimes, a transit reveals more than the existence of a planet. As the planet crosses its star, some starlight passes through the planet's atmosphere. Different gases absorb different wavelengths. By analyzing the spectrum, astronomers can study the atmosphere. The planet becomes a natural laboratory. Its atmosphere leaves a fingerprint in the starlight. Some planets have produced surprisingly unusual atmospheric signals. Clouds, water vapor, sodium, potassium, carbon-bearing molecules, hydrogen and helium. The chemistry varies enormously. Some worlds may have atmospheres dominated by gases that would be completely unfamiliar in the sky of Earth. And then there are hot planets where the atmosphere is constantly being stripped away by the intense radiation of their host star. The star bombards the planet. The upper atmosphere heats. Gas escapes into space. Over time, the planet can lose a substantial amount of its atmosphere. Some exoplanets appear to possess enormous clouds of escaping gas trailing behind them. The planet becomes almost comet-like, a world orbiting a star, its atmosphere flowing away, a tail extending behind it. This is an extraordinary planetary state. The world is gradually losing itself. But perhaps one of the most unusual categories of stars involves something even more fundamental. A star whose brightness changes because of internal pulsations. Some stars expand and contract rhythmically. Their surfaces move inward and outward. Their brightness changes. These variable stars can act as cosmic clocks. Certain classes have predictable relationships between their pulsation periods and intrinsic brightness. Cepheid variables are particularly important. Their pulsations allow astronomers to estimate distances to other galaxies. A star changes brightness in a predictable way. Astronomers measure the period. The period tells them how bright the star really is. Comparing intrinsic brightness with observed brightness gives a distance estimate. A vibrating star becomes a cosmic measuring instrument. The universe is full of natural tools. We do not build them. We discover them. Some are explosions. Some are pulsations. Some are orbital motions. Some are gravitational distortions. Each one gives us a different way to measure the cosmos. And among variable stars, there are some that are extraordinarily unusual. A star may change brightness irregularly. Another may brighten because of surface spots. Another may undergo periodic eclipses. Some stars pulsate because of complex internal physics. Some appear to change because they are interacting with companions. The sky is not as static as it seems. If you could watch every star simultaneously over long enough periods, the entire sky would appear alive. Stars would brighten, fade, pulse, erupt, disappear, and occasionally, something completely new would appear. Now let us move toward a rare phenomenon involving a star and a planet. Imagine a planet orbiting extremely close to its star. Its year might last only a few days. The star dominates its sky. The planet is heated intensely. The atmosphere may expand. The surface may become molten. Some worlds are so hot that rock itself can vaporize. The atmosphere can contain vaporized minerals. Winds may carry these gases from the hot day side toward the cooler night side. On the night side, the material may condense. Then winds carry it again. the planet becomes a world of evaporating rock. These objects are rare not because hot planets are unknown, but because the most extreme combinations of temperature, composition, orbit, and atmospheric behavior occur only under specific circumstances. Some are called lava worlds. Their surfaces may contain enormous oceans of molten rock. Imagine standing there. There would be no Earth-like landscape, no trees, no oceans of liquid water, no clouds of familiar composition. Instead, a glowing horizon, molten rock, an enormous nearby star, and a sky filled with radiation. These worlds are inhospitable by any Earth-based standard, yet they reveal the diversity of planetary systems. Nature does not create only Earth-like planets. It creates worlds that push chemistry and physics to extremes. Now consider a planet with an enormous ring system. Saturn's rings are famous, but rings are not exclusive to Saturn. Other planets possess rings as well, but some exoplanets may have rings far larger than anything in our solar system. A young giant planet can possess a large disk of debris, dust, ice, rock, fragments from collisions. Over time, the material may settle into rings or eventually form moons. The early stages of planetary system formation can therefore produce enormous structures. Some ring systems may be transient. They may exist for only a relatively short astronomical period before particles are incorporated into moons or fall toward the planet. A ring system can therefore be another example of a temporary cosmic rarity, something that exists only during a particular stage of planetary evolution. Imagine watching a young planet surrounded by a vast disk. The planet itself is still forming. Its moons have not fully developed. Debris is everywhere. Collisions happen constantly. The system is chaotic. But over millions of years, gravity organizes the material. The disk becomes more structured. Moons appear, gaps form, rings evolve. The planetary system slowly settles. A rare configuration becomes a more familiar one. The universe is constantly moving from chaos toward structure and back again. Now imagine a moon that is not simply a piece of rock orbiting a planet. A moon with an ocean hidden beneath an icy surface. Worlds like Europa and Enceladus have attracted enormous scientific attention because their interiors may contain subsurface liquid water. The water is hidden. The surface is frozen. But tidal interactions with their host planets can generate internal heat. Gravity stretches the moon. The moon responds. Energy becomes heat. The ice remains on the surface. Beneath it, an ocean may persist. This is one of the most intriguing possibilities in planetary science. An ocean hidden beneath kilometers of ice. No sunlight reaches it directly, yet chemical energy may exist. Hydrothermal processes may occur. On Earth, life thrives in environments that receive no sunlight, including ecosystems around deep-sea hydrothermal vents. So a hidden ocean raises an extraordinary question. Could life exist in darkness? We do not know, but the possibility has transformed our understanding of where habitable environments might exist. Perhaps life does not require a planet with a surface like Earth. Perhaps it only requires chemistry, energy, and a stable environment. A moon can be frozen on the outside and potentially active inside. A world can look dead from the surface while containing an enormous hidden ocean. This is another reminder that appearances can be deceptive. Space is full of hidden interiors, hidden oceans, hidden black holes, hidden matter, hidden atmospheres, and hidden histories. The rarest objects are often the ones that require us to look beneath the surface. Now let us return to the stars. There are stars that contain extremely unusual amounts of particular elements. Some appear enriched in carbon. Some have unusual iron abundances. Some contain strange combinations of elements that may have been inherited from ancient stellar explosions. These chemical peculiarities can reveal interactions. A star may have been polluted by material from a companion. It may have formed from gas enriched by a particular type of supernova. It may have undergone unusual internal mixing. Its atmosphere becomes a record. Astronomers use spectroscopy to read that record. Every element leaves characteristic patterns in light. Hydrogen produces one set of spectral signatures, helium another. Iron produces many. Calcium, sodium, magnesium, carbon, oxygen. Each contributes to the spectrum. A star's light can therefore be decomposed into a chemical fingerprint. Imagine receiving only light from an object billions of kilometers away. You cannot touch it. You cannot collect a sample. You cannot travel there. Yet by splitting its light into a spectrum, you can determine what elements are present. Light becomes a messenger. It crosses enormous distances carrying information. And the rarer the chemical signature, the more interesting the star may become. Some stars preserve evidence of ancient nucleosynthesis. They are cosmic archaeological sites. Now, one particularly intriguing category is the chemically peculiar star. These stars can have surface abundances that differ dramatically from ordinary stars. Magnetic fields may influence the movement of elements in their atmospheres. Some elements can become concentrated in particular regions. The star's spectrum changes. As the star rotates, different chemical patches may rotate into and out of view. The observed brightness or spectral properties can vary. Imagine a star whose surface is not chemically uniform. Instead, it has patches. One region rich in one element, another region enriched in another. The star rotates. Different regions face Earth. The light changes. A distant stellar surface becomes dynamic. The star may appear to pulse or vary even though the underlying process is simply rotation combined with chemical structure. Again, the universe is more complicated than a simple glowing sphere. Stars have surfaces, magnetic fields, atmospheres, winds, rotation, companions, and internal layers. Each contributes to the star's behavior. Now imagine a star with a magnetic field strong enough to create enormous spots. Sunspots exist on the sun, but some stars have far more powerful magnetic activity. Their surfaces can produce giant flares. These stellar flares can release tremendous amounts of energy. If a planet is orbiting very close to such a star, the consequences could be severe. Radiation can strip atmospheric molecules. High-energy particles can bombard the planet. The environment can become extremely hostile. Some stars are therefore rare laboratories for understanding planetary habitability. A planet's environment depends not only on the planet itself. It depends on the star's age, temperature, magnetic activity, flare rate, radiation, and long-term stability. A planet can sit in what appears to be a suitable orbital distance and still experience a harsh environment if its star is unusually active. This is why finding a habitable world requires much more than finding liquid water. The entire star-planet relationship matters. And perhaps the rarest planetary systems are those where many favorable conditions occur simultaneously. A stable star, a suitable orbit, a long-lived atmosphere, liquid water, chemical ingredients, protection from excessive radiation, and enough time for complex chemistry to develop. The universe contains an enormous number of planets. But the exact combination of conditions needed for a particular kind of world may be much rarer. We do not yet know how rare. That question remains open, and perhaps somewhere in the galaxy, a planet exists where the conditions are extraordinarily similar to those that allowed life to flourish on Earth. Perhaps another world has its own atmosphere, its own oceans, its own clouds, its own seasons, and perhaps something is looking upward from that world tonight. Perhaps another observer is wondering whether anyone else exists. The universe is large enough for the possibility to remain open. Now, as part 2 slowly comes toward its end, let us pull back once more. The individual stars become smaller. The binary systems become tiny points. The pulsars become invisible. The black holes disappear into the darkness. The galaxies become distant lights, and the cosmic web begins to surround everything. We have traveled through rare stars, stars stripped by winds, rapidly rotating stars, binary systems, stellar mergers, hidden black holes, accreting black holes, quasars, blazars, variable stars, hot exoplanets, evaporating worlds, young ring systems, icy moons, chemically peculiar stars, and many other unusual states of matter and energy. But this is only the beginning, because the universe becomes even stranger when we move closer to the most extreme stellar remnants. There are neutron stars that rotate hundreds of times per second. There are magnetic fields that dwarf anything on Earth. There are binary systems where matter flows from one star to another. There are collisions that shake space-time itself. There are explosions that briefly transform the sky. And there are objects so dense that ordinary intuition breaks down completely. In the next part, we will move deeper into that extreme universe. We will spend more time with pulsars and magnetars. We will explore stars that collapse. We will follow gravitational waves through space. We will watch 2 dead stars spiral together. And we will drift towards some of the rarest stellar remnants and most violent events known to science. For now, though, everything is quiet. Somewhere, a pulsar turns. Another pulse crosses the darkness. A distant magnetar waits. A white dwarf slowly cools. A binary star continues its ancient orbit. A black hole remains invisible. A planet circles a distant sun. And an ancient star continues shining after surviving for billions of years. None of them know that we are watching. They do not need to. The universe simply continues. Slowly, silently, without hurry. And perhaps you can allow yourself to do the same. Let your thoughts become lighter. Let the distant stars become softer. Imagine yourself drifting between galaxies, surrounded by darkness and scattered points of ancient light. There is nothing you need to solve tonight, nothing you need to remember. The universe is already carrying the story. All you need to do is listen. And somewhere far beyond the Milky Way, another rare object is shining. Its light has begun a journey. Perhaps that light will travel for millions of years, perhaps billions, and perhaps one distant day it will arrive here. Until then, it will simply continue through the darkness, quietly, patiently, just like the universe itself. The universe around us is becoming darker now. The familiar stars of the night sky have faded into the distance, and we are drifting toward a place where ordinary ideas about matter begin to break down. We are moving toward the remnants of stars, objects that were once enormous, objects that once burned with temperatures of millions of degrees, objects that once lived surrounded by oceans of plasma, and now, after the violent endings of their former lives, some have become tiny, dense, and extraordinarily strange. A neutron star can be smaller than a city while containing more mass than the sun. A magnetar can possess a magnetic field so powerful that it changes the behavior of matter around it. A pulsar can rotate hundreds of times every second. Two neutron stars can collide and shake space-time itself. And sometimes, the aftermath of these events leaves behind objects that are even more difficult to understand. Tonight, we are going deeper into that world. Imagine that we are approaching a neutron star from far away. At first, it looks like a small point of light, but as we come closer, the scale becomes difficult to comprehend. The star may be only about 20 kilometers across. That is roughly the width of a city, yet its mass can exceed that of the sun. The gravity at its surface is extraordinarily strong. Matter has been compressed beyond anything that can exist naturally on Earth. The familiar structure of atoms has essentially been destroyed. There are no ordinary rocks, no oceans, no mountains in the familiar sense. Instead, there is matter compressed under conditions so extreme that nuclear physics becomes the language required to describe it. The outer crust is believed to contain an incredibly dense lattice of atomic nuclei surrounded by electrons. As we move deeper, the conditions become even more extreme. Nuclei become increasingly packed. Neutrons become more abundant. At still greater depths, physicists are not completely certain what the interior looks like. Perhaps there are exotic states of nuclear matter. Perhaps strange particles appear. Perhaps the neutrons themselves exist in unusual quantum states. Perhaps even more exotic forms of matter exist in the deepest core. This uncertainty makes neutron stars more than astronomical objects. They are laboratories, but they are laboratories we cannot visit. We cannot place a thermometer inside one. We cannot take a sample. We cannot drill into the crust. We can only observe their effects, their radiation, their rotation, their gravitational fields, their collisions, and sometimes the vibrations of their surfaces. One of the rarest and most useful neutron stars is a pulsar whose rotation is extraordinarily stable. Some pulsars behave almost like clocks floating through space. Their pulses arrive at regular intervals. The timing can be measured with incredible precision. For astronomers, this stability becomes useful. A pulsar can act as a natural reference point. If its timing changes slightly, something may have influenced it. Perhaps a planet, perhaps a companion star, perhaps another neutron star, perhaps a disturbance in space-time. Imagine a lighthouse rotating in perfect darkness. Every rotation sends a beam outward. The beam crosses the universe. It passes through interstellar space. It continues toward Earth. And every time the beam sweeps across our planet, radio telescopes detect a pulse. Tick, tick, tick. Not a clock made by humans. A clock created by the collapse of a star. Some pulsars rotate only a few times each second. Others rotate much faster. Millisecond pulsars can spin hundreds of times per second. The surface is traveling at enormous speeds, and yet the star remains intact. Its gravity is powerful enough to hold itself together despite the rapid rotation. The stability is astonishing. Imagine a sphere containing more mass than the sun rotating hundreds of times every second. The universe allows this, and it does so naturally. One particularly unusual possibility arises when two pulsars orbit one another. A binary pulsar system, two compact objects moving through space. Each may emit pulses. Their orbits can be measured. Their pulses can be timed. And because the system is so precise, astronomers can observe effects predicted by general relativity. The orbit can slowly change. Energy can be carried away through gravitational waves. The system becomes a natural experiment in gravity. No laboratory on Earth can reproduce the same conditions, but the universe can. It creates two neutron stars. It places them in orbit. It lets them circle one another for millions or billions of years. And then it allows us to observe the result. One famous binary pulsar system provided some of the earliest indirect evidence for gravitational waves. The stars were losing orbital energy. Their separation was changing. The observed behavior matched predictions from Einstein's theory. The universe was whispering through gravity long before humans learned how to directly listen for those whispers. Then, decades later, gravitational waves were directly detected. The first direct detection came from the merger of black holes. For the first time, humanity was not simply seeing the universe. We were hearing space-time itself. The signal was incredibly faint by the time it reached Earth. It had traveled billions of light years. The original event involved black holes orbiting each other. They spiraled inward. Their speeds increased. Their gravitational fields interacted. And finally, they merged. The resulting black hole was larger than either original black hole. A portion of the total mass energy was radiated away as gravitational waves. The waves traveled outward at the speed of light. They crossed intergalactic space. They passed through galaxies. They passed through our own Milky Way. Eventually, they reached Earth. The physical change they caused in the distances measured by the detectors was extraordinarily tiny, much smaller than an atomic nucleus across the scale of the detector. Yet instruments could measure it. Humanity had developed technology sensitive enough to detect a disturbance in space-time caused by two black holes merging billions of light years away. That is one of the strangest achievements in science. The universe can move mountains in gravity. We detect the motion through a change smaller than the size of a proton. Now imagine the gravitational waves themselves. They are not ordinary sound. Space does not have to be filled with air for them to travel. They are ripples in space-time. As they pass through an object, distances stretch and compress. The effect is incredibly small, but it is real. A gravitational wave can begin in one of the most violent events imaginable and end as an almost imperceptible change in a detector on Earth. And the universe is constantly producing gravitational waves. Some are strong enough to detect. Others are far too weak. Some may come from merging black holes. Some from neutron stars. Some from asymmetric rotating objects. Some from events that occurred in the very early universe. The rarest signals may still be waiting to be detected. Now imagine two neutron stars again. They are much smaller than ordinary stars, but their gravitational fields are immense. They orbit one another. The orbit tightens. The gravitational waves grow stronger. The final seconds become incredibly energetic. The stars deform. Their shapes respond to one another's gravity. Matter can be squeezed and stretched. Then they collide. The merger may produce a short gamma-ray burst. It may produce a kilonova. A kilonova is a transient astronomical event associated with the merger of compact objects, particularly neutron stars. For a short time, the event can glow with enormous brightness. It may produce heavy elements through rapid neutron capture. Material is expelled into space. The debris expands. It cools. As it cools, newly formed heavy elements contribute to the opacity and color of the transient. The event fades, but its material remains. Perhaps some of that material becomes part of future stars. Perhaps some enters a planet. Perhaps some eventually becomes part of life. Again, cosmic destruction becomes cosmic creation. Now let us approach a magnetar. At first, we see only a tiny source. but the magnetic field surrounding it is immense. A magnetar is a neutron star whose magnetic field is among the strongest known. The magnetic field can be millions or billions of times stronger than the strongest fields humans routinely create. At sufficiently close distances, the field would dominate the environment. Magnetic stresses accumulate in the crust. The crust is incredibly dense, yet it can still fracture. A sudden rearrangement can release enormous energy. This is called a starquake. The idea sounds almost poetic. A quake on the surface of a dead star. But this is not a small geological event. It occurs on an object with extraordinary density and gravity. The release can produce powerful bursts of X-rays and gamma rays. The magnetar briefly becomes an intense source of high-energy radiation. Then the event ends. The star continues rotating. Another flare may occur years later, or decades later, or perhaps not during human observation at all. Some magnetars are more active than others. Some show repeated bursts. Some experience giant flares. And because magnetars are relatively rare, each one is valuable. They allow astronomers to study matter under extreme conditions. They may also help us understand how neutron stars evolve. A neutron star can be born with an enormous magnetic field. Over time, the field can decay. The star may transition into a quieter state. Eventually, it may become difficult to distinguish from other neutron stars. The universe does not have sharp boundaries between categories. Objects evolve. A star can pass through different phases. The same object can be classified differently at different times. A young neutron star may be an energetic pulsar. A highly magnetized one may be a magnetar. An older one may become much quieter. Astronomical categories are often snapshots of a continuous process. Now imagine a neutron star spinning so quickly that it approaches its breakup speed. There is a limit. If the surface rotates too rapidly, material could be thrown away from the equator. The star must balance gravity against rotational forces. Some neutron stars are among the fastest rotating objects known. Their rotation is a direct consequence of angular momentum conservation. When a massive star collapses, its radius becomes dramatically smaller. If its angular momentum remains similar, its rotation speeds up. This is the same principle as an ice skater pulling in their arms and spinning faster. But a neutron star takes this principle to an extraordinary extreme. A star hundreds of thousands or millions of kilometers across can collapse to a sphere only tens of kilometers wide. Its rotation can accelerate enormously. A slow rotation becomes rapid. Rapid becomes incredibly rapid. And eventually, the object becomes a cosmic spinner. Now let us move toward a rarer possibility. A neutron star with a planet. We have already considered pulsar planets. But imagine a world orbiting a neutron star that was born from a supernova. The planet may have survived the explosion, or it may have formed afterward from material around the remnant. The environment would be profoundly different from Earth. The host is no longer an ordinary star. The neutron star may emit beams of radiation. The radiation may be energetic. The planet's surface could experience conditions unlike anything in our solar system. Yet a planet exists. A world has somehow found itself orbiting a stellar corpse. This reminds us that planetary systems can survive extraordinary histories. The formation of planets is not limited to calm environments around stable stars. Nature can build worlds in surprising places. Now consider a star that is not a neutron star and not a black hole. A white dwarf. White dwarfs are much larger than neutron stars, but still extremely dense. A typical white dwarf may be similar in size to Earth. Its mass can be comparable to the Sun. Its gravity compresses matter strongly. But there is another strange property. A white dwarf is supported primarily by electron degeneracy pressure. Quantum mechanics helps prevent the star from collapsing further. This is one of the most remarkable examples of quantum physics shaping an astronomical object. The star is no longer supported by ordinary nuclear fusion. Instead, quantum mechanical rules resist gravitational collapse. The universe has created a star-sized object whose stability depends on the behavior of electrons under extreme compression. And there is a limit to how much mass a white dwarf can support. This is known as the Chandrasekhar limit. If a white dwarf approaches roughly 1.4 times the mass of the Sun, depending on composition and conditions, electron degeneracy pressure can no longer support it in the same way. The star becomes unstable. That boundary is fundamental. A little more mass can dramatically change the fate of the object. And in binary systems, a white dwarf can gain material from its companion. This creates a pathway toward a thermonuclear explosion. The star becomes heavier. The pressure rises. The temperature rises. Eventually, runaway nuclear burning can occur. The white dwarf may be destroyed. A Type I supernova can result. These explosions are rare but enormously useful. Their brightness can help astronomers measure distances across the universe. But the physics behind them is complicated. Not every white dwarf that gains mass necessarily explodes in exactly the same way. Different pathways may exist. Some systems may involve the merger of two white dwarfs, two dead stellar cores, two remnants of stars. They spiral together. The gravitational waves grow. The orbit shrinks. The stars approach. And then the merger occurs. Depending on their masses and composition, the outcome can vary. They may form a more massive white dwarf. They may undergo a thermonuclear explosion, or they may collapse under certain conditions. The universe gives us many possible endings. Now imagine two white dwarfs orbiting each other so closely that they complete an orbit in only minutes. The system would be extremely compact. The stars would be moving rapidly. Gravitational radiation would carry energy away. The orbital period would slowly decrease. Eventually, the system could merge. Such binaries are valuable sources of low-frequency gravitational waves. Future space-based gravitational wave observatories may be able to detect many more of these systems. There may be enormous populations of compact binaries that are currently invisible to traditional telescopes. This is another theme of modern astronomy. There is not one universe. There are many ways of observing the same universe. Visible light reveals one layer. Radio reveals another. X-rays reveal another. Gamma rays reveal another. Gravitational waves reveal another. Neutrinos reveal another. Each messenger shows us a different side of reality. And some of the rarest things become visible only when we use the right messenger. Neutrinos are particularly fascinating. They are tiny particles that interact extremely weakly with matter. They can travel through enormous amounts of material without being stopped. A neutrino produced in the center of a star can escape much more easily than ordinary light. This makes neutrinos valuable messengers from extreme environments. When a massive star undergoes core collapse, enormous numbers of neutrinos can be produced. They escape. They travel through the star. They leave the explosion. They pass through planets. They pass through Earth. Most pass straight through without interacting. A detector deep underground may occasionally record one. Imagine a particle passing through your body right now. Perhaps thousands. Perhaps millions. Perhaps far more. You would not feel them. They pass through. The universe is constantly filled with particles that barely interact with us. And yet, occasionally, one leaves a detectable trace. A neutrino can carry information from regions that light cannot easily escape. That makes neutrino astronomy especially powerful. We can learn about stellar cores, supernovae, the sun, cosmic ray interactions, active galaxies, and perhaps unknown sources. A particularly rare event would be the detection of neutrinos associated with a nearby supernova. A massive star dies. A burst of neutrinos travels outward. The particles arrive before or around the time electromagnetic light becomes visible. Detectors around Earth record the signal. Suddenly, astronomers know that something enormous has happened. The neutrinos have arrived carrying information from the collapsing core. A stellar death becomes visible through particles rather than light. This is multi-messenger astronomy. The same event can be observed through photons, gravitational waves, neutrinos, and other signals. Each messenger tells part of the story. Now imagine something even more elusive. A cosmic ray colliding with the atmosphere creates a cascade of particles. Among those secondary particles are muons. They reach Earth's surface. Some pass through buildings. Some pass through mountains. They are created high in the atmosphere and travel downward. These particles are constantly arriving. We live inside a cosmic particle environment without noticing it. Space is not empty. Even the apparently empty space between stars contains particles. Gas, dust, plasma, radiation, magnetic fields, neutrinos, cosmic rays. The universe is full of invisible traffic. The darkness is active. Now let us return to black holes. A black hole is defined by an event horizon. Crossing the event horizon means entering a region from which no signal can escape to the outside universe. But the event horizon itself is not a physical surface. It is a boundary in space-time, a place where escape becomes impossible. For a distant observer, matter falling toward a black hole appears increasingly slowed and redshifted as it approaches the horizon. The actual physics from the perspective of the falling object is different, but the key idea is that the event horizon marks a one-way boundary. Beyond it, our ordinary ability to receive information ends. This makes black holes profoundly mysterious. We can observe their effects. We can observe accretion disks, jets, gravitational waves, stellar orbits, but the interior remains inaccessible. The black hole hides itself behind the horizon, and among black holes, there may be rare intermediate mass black holes. These would occupy a middle range between stellar mass black holes and the supermassive black holes found in galactic centers. They are difficult to detect. Their existence is supported by some observations, but confirming individual examples can be challenging. If such black holes are found in significant numbers, they could help explain how supermassive black holes grew. Perhaps small black holes merged repeatedly. Perhaps some intermediate mass black holes formed in dense stellar environments. Perhaps they are remnants of massive early stars. The universe may contain a population of these objects that we are only beginning to uncover. And then there are primordial black holes. These are hypothetical black holes that could have formed in the extremely early universe from density fluctuations. Unlike ordinary black holes, they would not necessarily have formed from stars. They could, in principle, have a wide range of masses. Some theoretical possibilities would make them extraordinarily small. Others could be much larger. There is no confirmed detection of primordial black holes, but they remain interesting because they could potentially connect black hole physics with cosmology. Perhaps some fraction of dark matter could consist of primordial black holes. Perhaps not. The question remains open. Again, rarity and uncertainty become intertwined. Something hypothetical can be one of the rarest things imaginable because we do not yet know whether it exists at all. Now consider a phenomenon predicted by physics that may occur around black holes: Hawking radiation. According to quantum field theory in curved spacetime, black holes can emit thermal radiation and gradually lose mass. For large astrophysical black holes, this radiation is extraordinarily weak. The effect is far too small to observe directly with current technology. But in theory, black holes are not completely black. They can slowly evaporate. A black hole can have a lifetime vastly longer than the current age of the universe. For a stellar mass black hole, the evaporation time is fantastically long, but smaller black holes would evaporate faster. If primordial black holes with sufficiently small masses existed, some could potentially be nearing the end of their lives today. Their final stages could involve powerful bursts of radiation. None have been confirmed, but the possibility remains one of the most intriguing intersections of quantum mechanics, gravity, and cosmology. A black hole slowly disappearing. Not quickly, not dramatically, but over incomprehensibly long periods. The universe can create objects that outlive almost everything else. And then, according to theory, even those objects may eventually vanish. Imagine a universe trillions upon trillions of years in the future. Stars have long stopped forming. Galaxies have changed. Planets are dark. White dwarfs have cooled. Black holes dominate. And even black holes eventually evaporate. The final stages of black hole evaporation would represent one of the most extreme endings imaginable. But that future is so distant that it almost becomes impossible to call it a date. It is more like a direction in time. The universe is still young compared with that future. Tonight, stars are shining. Supernovae are exploding. Planets are forming. Black holes are growing. Neutron stars are merging. The universe is still active. And that makes the rare events we observe today even more remarkable. They are moments in an enormous cosmic era. Now imagine a very different rare object. A brown dwarf. It is sometimes described as a failed star. Brown dwarfs form more like stars than planets, but they do not have enough mass to sustain ordinary hydrogen fusion like the sun. They exist in the space between stars and planets. Some are cool and faint. Some have atmospheres filled with complex chemistry. Some may have clouds made from mineral particles. Their temperatures can be far below those of ordinary stars. Yet they are still massive enough to behave differently from planets. Brown dwarfs are difficult to observe because they can be very faint. The coolest examples are particularly challenging to find, and some may be isolated, drifting through space without a nearby star. A lonely brown dwarf. Not quite a star. Not quite a planet. A world-like object wandering through interstellar darkness. These objects remind us that nature does not always respect human categories. We like to divide things into boxes. Star, planet, moon, black hole. But the universe creates continuums. Objects can occupy transitional states. Mass determines what nuclear reactions are possible. Formation history influences composition. Age changes temperature. The boundaries become complicated. And sometimes, the most interesting objects are the ones sitting between categories. Now consider an even stranger possibility. A free-floating planetary mass object with no star. Some rogue planets may have been ejected from young planetary systems. A young system can be gravitationally chaotic. Planets interact. Orbits change. One world can be thrown outward. It escapes the gravitational influence of its original star. It becomes a traveler. A rogue planet may then spend billions of years moving through the galaxy. Its surface freezes. Its atmosphere may collapse, but internal heat could remain. Radioactive decay continues. Perhaps tidal heating is absent, but geothermal energy remains. If the planet is massive enough, an insulating atmosphere or thick ice layer could retain heat. Some scientists have considered whether subsurface oceans might persist on certain rogue worlds. If so, a planet wandering alone through the galaxy could potentially maintain a hidden liquid environment. A world with no sun. A world whose surface is frozen. A world whose interior remains warm. It sounds like science fiction, yet physics does not immediately forbid it. The galaxy could contain enormous numbers of objects like this. They would be difficult to detect. We might only discover some through gravitational microlensing. A rogue planet passes between Earth and a distant background star. Its gravity bends the star's light. The star temporarily brightens. Then the event disappears. The planet continues moving. A cosmic fingerprint lasting perhaps hours or days. And then nothing. The star returns to normal. The planet vanishes into darkness again. This is one of the most beautiful forms of astronomical detection. We do not see the planet itself. We see what its gravity does to something behind it. The invisible becomes visible through influence. Now, as we drift farther into part 3, we are beginning to see a pattern. The rarest things are often connected. A massive star can become a neutron-star. A neutron-star can become a pulsar. A pulsar can become part of a binary. Two neutron stars can merge. Their merger can produce gravitational waves. It can create heavy elements. It can leave behind a black hole. That black hole may later merge with another black hole. The gravitational waves travel through the universe. The matter created in one event becomes part of another generation of stars. A single cosmic story can stretch across billions of years. Nothing exists in complete isolation. Stars influence galaxies. Galaxies influence stars. Black holes influence their environments. Planets evolve with their stars. Matter moves between generations. The universe is one enormous connected system, and some of its rarest events are turning points. Moments when one state becomes another. A star becomes a remnant. Two remnants become one. A planet loses its atmosphere. A white dwarf explodes. A black hole grows. A galaxy becomes active. A particle reaches Earth. Each event changes something. And perhaps the rarest things are those moments when the universe changes direction. Now, somewhere in a distant galaxy, a neutron star may be rotating silently. Its magnetic field surrounds it. Its pulse travels outward. The pulse crosses the darkness. It passes a distant planet. It travels beyond its galaxy. And perhaps one tiny fraction of that radiation eventually reaches Earth. A telescope detects it. A computer records it. An astronomer sees the pattern. A star that died long ago has spoken, not with words, with light, with timing, with physics. And we listen. This is what astronomy really is. Listening to the universe. The stars do not speak our language. They speak through radiation, gravity, particles, motion, spectra, and time. Tonight, we are simply listening to a few of their quietest stories. There are still many more ahead. There are stranger stars, more unusual black holes, rare planetary environments, mysterious cosmic explosions, unusual galaxies, and objects whose existence challenges the boundaries of what we thought was possible. But for now, let the journey slow. Imagine the neutron stars becoming distant points of light, the magnetars fading into the darkness, the gravitational waves moving silently through space. the black holes disappearing beyond our sight, the planets becoming tiny shadows around distant stars, the ancient photons continuing their journeys, and you are floating quietly among them. No destination, no urgency, just space, deep space, dark space, peaceful space. The universe is enormous enough that there is always somewhere farther to go. And in the next part, we will follow that darkness toward one of the most mysterious families of objects in existence. Black holes. Not simply the black holes themselves, but the rare things that happen around them. Stars torn apart, jets stretching across galaxies, accretion disks glowing with enormous energy, strange orbits, gravitational lenses, merging black holes, and perhaps some of the most extreme environments known anywhere. For now, though, allow your thoughts to become quiet. A pulsar continues its rhythm. A magnetar slowly turns. A white dwarf cools. A black hole waits. A rogue planet drifts. And somewhere far beyond everything we can see, two distant objects are moving toward one another. They may not meet for millions of years, but gravity has already begun the journey. Slowly, patiently, silently, just as the universe has always moved. And as the stars continue their ancient stories, you can simply rest here for a while. The cosmos has no need to hurry. Neither do you. We are entering regions where gravity becomes so powerful that light itself can be trapped, where stars can be stretched into streams of matter, where galaxies can shine brighter than billions of ordinary suns, and where the empty spaces between galaxies can become enormous cosmic deserts. The universe is not simply a collection of stars scattered across darkness. It is a vast architecture. There are galaxies gathered into groups, groups gathered into clusters, clusters connected by enormous filaments. And between these structures are immense regions containing remarkably little matter. Some of the rarest things in space are not objects at all. They are unusual arrangements of objects, rare alignments, rare environments, rare moments, and sometimes rarity comes from the sheer scale of what we are observing. Imagine drifting toward a galaxy cluster. At first, you might see only a faint concentration of light, but as you approach, thousands of galaxies begin to appear. Spiral galaxies, elliptical galaxies, irregular galaxies, galaxies that have collided, galaxies that are still forming stars, galaxies whose brightest stars disappeared billions of years ago. The cluster is enormous. Its total mass is far greater than what we can see in stars and gas alone. Much of its mass is believed to be dark matter, invisible, yet gravitationally powerful. And then something extraordinary happens. A galaxy far behind the cluster appears distorted. Its light is being bent. The cluster acts like a gigantic gravitational lens. The background galaxy may appear stretched into arcs. Sometimes it can appear as multiple images. Sometimes an almost perfect ring can form. A gravitational Einstein ring. The alignment must be remarkably precise. A foreground mass, a distant background source, and Earth, all arranged in the right geometry. When the alignment is almost perfect, the light from the background object can be bent around the foreground mass and form a ring-like structure. The universe has created a telescope without building one. Gravity itself becomes the lens. A cluster of galaxies can magnify something so distant that we would otherwise struggle to detect it. Ancient galaxies can become visible. Tiny features can be enlarged. Light that began its journey billions of years ago can be redirected toward us. The effect is beautiful, but it is also scientifically valuable. A gravitational lens does more than magnify. It tells us about the mass of the foreground object. Even invisible dark matter can reveal itself through the way it bends light. We may not see the dark matter, but we can see the shape it creates in the light of distant galaxies. Imagine the universe as a giant sheet of fabric. Place a heavy object on that fabric. The surface bends. Now send a beam across it. The path changes. Space itself can curve. The real universe is more complicated than this simple picture, but the basic idea helps us imagine what gravity does. A galaxy cluster bends space-time. Light follows that curved geometry. A distant galaxy appears in a distorted position. The cosmos is acting like a lens. And occasionally, the geometry becomes so precise that the result is extraordinarily rare. A nearly perfect Einstein ring. A circle of ancient light surrounding a foreground object. The ring may look delicate, but behind it is enormous gravitational power. Now imagine something even rarer. A gravitational lens that temporarily brightens a tiny distant object. A star passes behind another object from our perspective. The foreground object bends and magnifies the light. For a brief period, the background star becomes brighter. This is gravitational microlensing. Unlike ordinary lensing by a galaxy cluster, the foreground object might be a single star, planet, black hole, or other compact object. The event can be brief. Sometimes the lens itself remains invisible. Astronomers simply observe the temporary change in brightness. Then the event disappears. The background star returns to its original brightness. The lens continues moving through space. This technique can reveal objects that emit little or no light. A rogue planet can pass through the right alignment. A dark compact object can betray itself. A distant star can become temporarily magnified. Again, gravity becomes the messenger. Now imagine a black hole drifting alone through the Milky Way. It has no companion, no bright accretion disk, no obvious jet, no glowing material around it. It is almost completely dark. How could we find it? Perhaps one day it passes in front of a background star. Its gravitational field bends and magnifies the star's light. The star brightens. The position of the star may shift slightly. Astronomers detect the disturbance. There is no visible object responsible, only gravity. This is one of the most fascinating possibilities in astronomy. A black hole that has been wandering silently through our galaxy for millions of years could pass almost unnoticed. And then, for a short period, its presence could become visible through the distortion of another star. The universe can hide an object for billions of years, then reveal it through a momentary change in light. Now let us move toward an even more violent interaction. Imagine a star passing too close to a supermassive black hole. The star is held together by its own gravity, but the black hole's tidal forces are enormous. The side of the star closest to the black hole experiences a stronger gravitational pull than the side farther away. The difference becomes overwhelming. The star stretches. It becomes elongated. Then it begins to break apart. The event is known as a tidal disruption event. A star is literally torn apart by a black hole. Gas streams away. Some material escapes. Some material becomes gravitationally bound and falls toward the black hole. An accretion disk can form. Radiation is released. For a time, the black hole becomes dramatically brighter. The event may be visible across enormous distances. Imagine watching from far away. A galaxy that appeared relatively quiet suddenly develops a brilliant flare from its center. The flare brightens, then gradually fades. Something happened. A star wandered too close. The black hole won. The star's material became part of the black hole's environment. This is not an ordinary stellar explosion. The star did not collapse from within. It was destroyed from the outside by differential gravity. The process is almost unimaginably violent, but it also provides a natural experiment. By observing the changing light, astronomers can study the black hole's environment. They can learn about the accretion process. They can estimate properties of the black hole, and they can understand how matter behaves when pushed to extreme gravitational conditions. Tidal disruption events are not common. A supermassive black hole needs to encounter a star in just the right way. Too far away, and the star survives. Too close, and it may be swallowed without producing the same observable signature. The geometry matters. The star's structure matters. The black hole's mass matters. The encounter must happen within a certain range. Rarity emerges from the conditions. Now imagine a black hole that spins. A spinning black hole drags space-time around with it. This phenomenon is known as frame dragging. The black hole does not simply sit in space. Its rotation affects the surrounding space-time. Near the black hole, this effect can become extreme. There is a region called the ergosphere outside the event horizon of a rotating black hole. Inside the ergosphere, space-time is effectively dragged around the black hole. An object cannot remain completely stationary relative to distant space. Everything is forced to participate in the dragging effect. It is difficult to imagine. The black hole spins. Space-time responds. Nearby matter is carried along. The geometry itself becomes dynamic. And in theory, energy can be extracted from a rotating black hole through processes associated with the ergosphere. One proposed mechanism is the Penrose process. Another involves electromagnetic fields and accretion systems. The important idea is that a rotating black hole contains rotational energy. It is possible, in principle, for some of that energy to be transferred outward. This may help explain the enormous power of some astrophysical jets. A tiny region near a black hole can influence structures extending far beyond the host galaxy. Imagine a supermassive black hole millions or billions of times more massive than the Sun. It is surrounded by a disk of gas. Magnetic fields become organized. Matter spirals inward. Powerful jets emerge. The jets can extend thousands or even millions of light years in extreme cases. The engine is incredibly compact compared with the structure it creates. A black hole can be smaller than our solar system while influencing a region larger than a galaxy. This is one of the great scale contrasts of the universe. Tiny engine, enormous consequences, and some jets become so powerful that they carve enormous cavities into the hot gas surrounding a galaxy cluster. The jet deposits energy. The surrounding plasma is pushed away. A bubble forms, then another. Over time, the central black hole can regulate the environment around it. This is known as AGN feedback when referring to active galactic nuclei. The black hole is not simply consuming matter. It can also influence whether its galaxy forms new stars. Energy from the central engine can heat gas. Heated gas may become less likely to collapse into new stars. The black hole therefore participates in the evolution of its entire galaxy. The connection between a supermassive black hole and its host galaxy is one of the most fascinating relationships in astrophysics. The black hole may contain only a tiny fraction of the galaxy's total mass, yet its activity can influence enormous quantities of gas. A small central object can shape a huge cosmic environment. Now imagine a galaxy whose central black hole is unusually quiet. There is little gas falling inward. The center is dim. The black hole is still enormous, but it is not actively feeding. Our own Milky Way has a supermassive black hole at its center, known as Sagittarius A star. It is relatively quiet compared with the most powerful active galactic nuclei, but it is not completely inactive. Gas and stars orbit around it. Occasionally, material approaches the central region. Flares can occur. The black hole's gravitational influence shapes the orbits of nearby stars. Some stars orbit extraordinarily close to the galactic center. Their motion provides a way to measure the black hole. We do not see the black hole itself in ordinary visible light. Instead, we track stars moving around an invisible mass. Their orbits reveal what is there. One star in particular, often called S2, has been observed making close approaches to Sagittarius A star. Its orbit has allowed astronomers to test general relativity in the strong gravitational field near the galactic center. The star moves rapidly. Its path shifts slightly over time. Space-time around the black hole is not behaving exactly like ordinary Newtonian space. Einstein's theory predicts the deviations. Observations agree remarkably well. A star orbiting a black hole becomes a test particle for fundamental physics. Now move outward from the galactic center. The Milky Way is filled with hundreds of billions of stars. But even that enormous number is small compared with the scale of the observable universe. There are billions of galaxies, perhaps far more. Each galaxy contains stars. Many contain planets. Many contain black holes. Some contain enormous quantities of gas. Others contain almost no cold gas. Some are actively forming stars. Others have become quiet. And among them are extremely rare galaxies. Consider a galaxy that is almost completely devoid of dark matter. Such objects are unusual because dark matter is thought to play a major role in galaxy formation. Finding a galaxy with very little dark matter can challenge our understanding of how galaxies form and evolve. The measurements are difficult. Mass can be hidden. Gas can influence motion. Distance estimates can be uncertain. But candidate systems have generated considerable interest. The possibility of a galaxy with unusually little dark matter reminds us that cosmic structures do not always follow the simplest patterns. Now imagine the opposite. A system dominated by dark matter. Almost invisible. Few stars. Very little ordinary matter. Yet gravitationally massive. Such an object would be difficult to see directly. We might discover it through gravitational effects on surrounding material. Dark galaxies, dark halos, and dark structures remain challenging areas of research. Perhaps the universe contains enormous quantities of matter that have not yet formed visible stars. Perhaps some dark structures are remnants of early cosmic formation. Perhaps some candidate objects have other explanations. The search continues. The mystery remains. Now imagine a galaxy with almost no new star formation. Its young, massive stars have disappeared. Its gas has been consumed or expelled. The galaxy becomes dominated by older stars. The light shifts toward redder wavelengths. It becomes what astronomers sometimes call a quiescent or passive galaxy. These galaxies can be enormous. Some contain trillions of stars, yet they are relatively quiet. No brilliant blue nurseries. No constant explosions of young stars. Just ancient stellar populations moving through space. The galaxy slowly ages. It may remain stable for billions of years. And somewhere inside its center, a supermassive black hole may sit quietly. A dormant giant at the heart of an ancient city of stars. Now let us go farther back in cosmic time. Imagine the universe when it was only a fraction of its current age. Galaxies were forming. Stars were appearing. The first heavy elements were beginning to spread through space. the universe looked nothing like it does today. The earliest galaxies are among the rarest things we can observe because their light is faint and has been traveling for most of cosmic history. When we see them, we are seeing ancient light. We are looking backward in time. A galaxy located billions of light years away is not being observed as it exists today. We see how it looked billions of years ago. The farther we look, the further back we see. A telescope becomes a time machine, not a machine that sends us into the past physically, but an instrument that collects ancient photons. A photon emitted long ago can travel across the universe. It eventually reaches a detector, and that photon carries information about the conditions that existed when it began its journey. Imagine a tiny particle of light leaving a young galaxy. The galaxy is still forming. Stars are exploding. Gas is collapsing. Black holes are growing. The photon leaves. It travels. Millions of years pass. Then hundreds of millions. Then billions. Eventually, the photon enters a telescope on Earth. A human being sees the resulting image. The ancient galaxy becomes visible. We are looking at something that existed before our planet had its current form. That is the strange intimacy of astronomy. The past is constantly arriving. Now imagine an even earlier source, one of the first generations of stars. Theoretical models suggest that the earliest stars, known as population 3 stars, formed from material containing almost exclusively hydrogen and helium, with only tiny amounts of heavier elements produced in the Big Bang. They would have been very different from stars like the Sun. Their lack of heavy elements could have allowed them to grow extremely massive. They may have lived short lives. They would have exploded or collapsed. They would have produced heavier elements that later generations of stars inherited. Yet direct observations of individual population 3 stars have not been confirmed. Their existence is strongly expected from cosmological models, but they remain elusive. If we could observe one directly, it would be like discovering a living fossil from the earliest era of stellar evolution. A star from the cosmic dawn. A star born before the universe had accumulated the chemical richness we see today. The first stars may have transformed their surroundings. Their ultraviolet radiation could have changed the state of intergalactic gas. Their explosions could have spread the first heavy elements. Their black hole remnants may have contributed to the growth of early supermassive black holes. In a sense, they were the universe's first chemical factories. Without them, planets like Earth could not exist. The carbon in our bodies, the oxygen we breathe, the iron in our blood, the calcium in our bones, the silicon in rocks. These elements were not present in the early universe in the quantities we see today. Stars made them. Stars scattered them. Later stars formed from enriched material. Planets formed from that material. Life emerged on at least one of those planets. And now, billions of years later, that life can look backward and wonder about the stars. The cycle is extraordinary. Matter becomes stars. Stars become elements. Elements become planets. Planets become environments. Environments produce life. Life studies stars. The universe has become capable of observing itself. Now, among galaxies, there are objects even more difficult to categorize. Consider a galaxy that contains an enormous amount of gas, but relatively few stars. Why has the gas not collapsed into stars? What processes are preventing star formation? Perhaps turbulence. Perhaps magnetic fields. Perhaps feedback from an active black hole. Perhaps the galaxy is in an unusual stage of evolution. These systems can provide clues about how galaxies transition between active and quiet phases. Then there are galaxies with extremely high star formation rates. Their interiors can be filled with dense clouds of gas. New stars form rapidly. Massive stars live briefly and explode. The galaxy can shine strongly in infrared wavelengths because dust absorbs starlight and re-radiates the energy. Some of these galaxies are known as starburst galaxies. They are not necessarily rare on cosmic timescales, but extreme examples are unusual. A galaxy can temporarily become a stellar factory. Imagine millions of stars forming over a relatively short period. The galaxy glows. Supernovae explode. Winds from young stars blow bubbles through the gas. The environment becomes turbulent, and eventually, the fuel begins to diminish. The starburst fades. The galaxy returns to a quieter state. Again, cosmic structures move through phases: birth, growth, activity, quiet, transformation, death, and perhaps rebirth. Now let us enter a cosmic void, a region of space hundreds of millions of light years across can contain remarkably few galaxies compared with the dense regions around it. These are cosmic voids. They are not completely empty. There is still dark matter. There may be diffuse gas. There may be tiny galaxies. But compared with the filaments and clusters around them, voids are extraordinarily sparse. Imagine traveling through one. For millions of light years, there may be very few galaxies nearby. The sky would still contain distant light, but the local cosmic neighborhood would be astonishingly empty. A void is not an absence of the universe. It is part of its structure. The cosmic web contains dense nodes and long filaments surrounding vast underdense regions. Gravity gradually pulled matter into denser areas. The voids became emptier. The filaments became richer. Galaxies formed along the structure. The universe developed a pattern on scales so large that the human mind struggles to visualize it. And yet the pattern began from tiny density variations in the early universe. Small differences. Over time, gravity amplified them. Matter gathered. Structures grew. Clusters formed. Voids expanded. The cosmic web emerged. A delicate pattern on a gigantic scale. Now imagine one of the most unusual possibilities within a cosmic void. A galaxy that appears to be unusually isolated. It may have no major neighbors, no obvious interaction, no large companion. It drifts through a sparse environment. Its evolution may be slower or different because there are fewer interactions. Galaxies are often shaped by their surroundings. A galaxy in a crowded cluster experiences many gravitational encounters. A galaxy in a void may experience far fewer. Environment becomes another factor in cosmic evolution. The universe is not uniform. Location matters. Just as climate affects life on Earth, cosmic environment affects galaxies. Now let us return to the enormous clusters. Inside a galaxy cluster, there may be gas heated to tens of millions of degrees. The gas is so hot that it emits strongly in X-rays. It is not empty space. It is a gigantic atmosphere surrounding hundreds or thousands of galaxies. The gas contains enormous amounts of matter. It can be heated by mergers, by shocks, by active galactic nuclei, by gravitational collapse. And sometimes, a supermassive black hole produces jets that carve cavities in this hot plasma. Imagine a bubble larger than a galaxy being inflated by a black hole. The jet travels outward. It pushes against the surrounding gas. A cavity forms. Then the jet changes direction or weakens. The bubble rises through the cluster. The black hole has effectively stirred the atmosphere of an entire galaxy cluster. This is a spectacular example of feedback across scales. A compact object influences a structure millions of light years across. Now imagine two galaxy clusters colliding. They approach each other at enormous speeds. Their galaxies mostly pass through without direct collisions because stars are separated by huge distances. But the gas interacts. Shock waves travel through the plasma. The dark matter halos interact gravitationally. The cluster's mass distribution changes. The collision can create enormous structures visible through X-rays and gravitational lensing. Cluster mergers are among the most energetic events in the universe. They take millions of years to unfold. Yet when viewed through telescopes, we can reconstruct their motion. The universe can turn entire collections of galaxies into laboratories for dark matter physics. Some famous cluster collisions have provided evidence that most of the mass behaves differently from ordinary gas. The gas slows through collisions. The dark matter behaves differently. The separation between the two components can be observed through gravitational lensing. This gives us a way to study the invisible. Dark matter cannot be photographed directly, but when galaxy clusters collide, the different behavior of gas and gravitational mass can reveal the hidden structure. The universe becomes its own experiment. Now imagine an even rarer alignment. A foreground galaxy cluster lensing a distant supernova. The supernova appears brighter than it otherwise would. Perhaps multiple images appear. Each image may arrive at a different time because the light travels along different paths through the gravitational field. A single explosion can therefore be seen more than once. The universe creates multiple copies of an event. Not truly copies. They are different light paths from the same event. One image may appear first. Another may appear later. The delay can be days, months, years. The effect depends on the geometry and gravitational potential. Imagine seeing the same cosmic explosion happen twice. You know the second appearance is not a new explosion. It is the old light arriving by a different route. This is gravitational time delay. It is another reminder that gravity affects not only where light travels, but also how long the journey appears from our perspective. Now imagine a supernova that becomes visible because of such a lens. The explosion occurs in a distant galaxy. The light travels toward Earth. A massive foreground structure bends the light. The signal becomes magnified. The supernova is detected. Without the lens, it might have been too faint. Gravity has amplified the message. This is one of the rarest and most beautiful collaborations between cosmic objects. One galaxy cluster helps us see another galaxy. The universe is constantly revealing itself through relationships. Now let us consider a strange kind of explosion. A fast blue optical transient. Some transient events brighten rapidly and fade quickly. They may not fit neatly into ordinary supernova categories. Some are associated with unusual stellar environments. Others may arise from extreme interactions. The exact origins of every unusual transient are not always understood. Astronomers continually discover new classes of short-lived events. This is important because the universe does not always announce its categories before we observe them. We may see something unusual first. Then researchers ask what it is. A new class can emerge from a single puzzling observation. The sky changes. A telescope detects it. Astronomers compare it with known events. It does not match. More observations follow. Eventually, a new physical explanation emerges. Astronomy is still discovering categories. The universe is not finished surprising us. And perhaps this is what makes the rarest things so fascinating. They remind us that our catalog of the universe is incomplete. We have mapped enormous numbers of galaxies. We have discovered thousands of exoplanets. We have observed black hole mergers. We have detected gravitational waves. We have measured the cosmic microwave background. And still, there are things we have never seen. Objects that may exist beyond our current detection limits. Events that happen too rarely. Signals that are too faint. Regions hidden behind dust. Phenomena that last for seconds. And perhaps entirely new classes of objects waiting for better instruments. Now imagine a telescope observing the sky continuously. Every minute, every second, across enormous regions. The number of transient events would be astonishing. Stars flare, asteroids move, supernovae appear, black hole systems brighten, neutron stars burst, gamma ray bursts flash. Some events last years, others seconds. Some may last only milliseconds. A cosmic fireworks display is happening constantly. We simply do not see most of it with our eyes. The night sky appears still because human perception operates on short timescales. The universe operates on many timescales simultaneously. Milliseconds, seconds, years, millions of years, billions of years. A gamma ray burst may transform in seconds. A star may live millions of years. A galaxy may evolve over billions. The universe contains all of these clocks at once, and we are learning how to listen to them. Now, somewhere beyond the Milky Way, a star is approaching the end of its life. It has burned through its fuel. Its core is changing. Its outer layers are unstable. Perhaps it will become a white dwarf. Perhaps a neutron star. Perhaps a black hole. Its final state depends on its mass and history. The star does not know what comes next. It simply follows the laws of physics. Gravity pulls inward. Pressure pushes outward. Nuclear reactions change. The balance shifts. Eventually, the old equilibrium ends. Something new appears. This is the central story of stellar evolution. Nothing stays unchanged. The universe is a place of transformation. Even the rarest objects are temporary. A magnetar will not remain a magnetar forever. A quasar will eventually become quiet. A starburst galaxy will eventually exhaust its fuel. A tidal disruption event will fade. A gravitational lensing alignment will end. A binary system will merge. A supernova will disappear. A cosmic structure that seems permanent is often simply long-lived compared with human experience. And perhaps that is why looking at the universe can be calming. Everything moves. Everything changes. Yet nothing requires our attention. The stars continue their journeys without asking anything from us. The galaxies drift. The planets orbit. The black holes rotate. The photons travel. The gravitational waves pass. And for a moment, we can simply watch. As part 4 comes toward its quiet ending, imagine yourself floating above a distant galaxy cluster. Below you, thousands of galaxies move through enormous darkness. Between them are vast regions of hot gas. Dark matter shapes the cluster invisibly. Jets rise from distant black holes. Light from ancient galaxies bends around the cluster. Far behind it, a supernova shines. Its light curves around the gravitational field. Some photons take one path. Others take another. Eventually, they reach a telescope. A scientist sees the event. The explosion that happened billions of years ago has become a few pixels on a screen. But those pixels contain history. A star lived. A star died. Its light traveled. Gravity bent it. And now, after all that time, someone saw it. That is the scale of the universe. A moment of death can become a message lasting billions of years. A single star can influence its surroundings. A black hole can shape a galaxy. A cluster can bend light. A tiny fluctuation can grow into a cosmic web. And a small planet can produce a species capable of wondering about all of it. So let the scale of the universe become quiet now. You do not need to hold on to every detail. You can simply imagine the distant galaxies becoming softer, the bright arcs of gravitational lenses fading into darkness, the hot cluster gas becoming a faint glow, the black holes becoming silent shadows, the ancient photons continuing their journey. And somewhere in that enormous darkness, another rare event is beginning. Perhaps a neutron star is spiraling toward another. Perhaps a star is approaching a black hole. Perhaps a distant galaxy is experiencing a burst of star formation. Perhaps a planet is crossing the face of a distant sun. Perhaps a gravitational wave is moving through space right now. It may have begun millions or billions of years ago, and perhaps it will pass through Earth without anyone noticing. Or perhaps one day, a detector will record it. A tiny signal, a tiny change, a whisper from an event unimaginably far away. The universe is full of whispers. We are simply learning how to hear them. And the journey is not finished. There are still rarer things waiting beyond the galaxies. Strange forms of matter, unusual cosmic explosions, ancient remnants, objects that exist only for moments, and perhaps phenomena that have never been seen before. So for now, drift quietly onward, past the galaxies, past the clusters, past the enormous cosmic voids, into the deeper darkness. The next part will take us towards some of the strangest transient events ever observed. Brief flashes that can outshine entire galaxies. Explosions that last only seconds. Objects that suddenly appear and disappear. And mysterious bursts whose origins can remain uncertain even after years of study. For now, though, breathe slowly. The stars are far away. The universe is vast, and there is nowhere you need to be. The galaxies can continue without you. The black holes can continue turning. The ancient light can continue traveling. And somewhere beyond the darkness, another rare story is already unfolding. Quietly, patiently, across the endless universe. We have already traveled past unusual stars, neutron stars, magnetars, black holes, gravitational lenses, ancient galaxies, enormous cosmic voids, and violent stellar remnants. But the deeper we go, the stranger the universe becomes. Because some of the rarest things in space are not objects that remain visible for millions of years. Some appear for only a few seconds. Some last for minutes. Some may exist for only a fraction of a second. A flash appears in the darkness. It releases an extraordinary amount of energy. Then it disappears. The universe becomes quiet again, and astronomers are left trying to understand what happened. Imagine looking at the night sky and seeing nothing unusual. Then suddenly, somewhere unimaginably far away, a burst of radiation begins. The event may have started billions of years ago. The energy travels through space. It crosses enormous distances, and eventually, a tiny portion reaches Earth. A detector records it. The signal may last only seconds, but those seconds can carry information from one of the most violent environments in existence. These are gamma-ray bursts. Gamma rays are the most energetic form of electromagnetic radiation. They are invisible to human eyes. Our atmosphere blocks much of this radiation, which protects life on Earth. But spacecraft above the atmosphere can detect it. And when a gamma-ray burst occurs, the signal can be extraordinary. Some gamma-ray bursts are associated with the collapse of massive stars. Others are associated with mergers of compact objects such as neutron stars. The physical details can differ, but the result can be an intense flash of high-energy radiation. Imagine a massive star reaching the end of its life. Its core collapses. The outer layers respond. A black hole or neutron-star may form. Powerful jets can emerge along the star's rotational axis. If one of those jets happens to point toward Earth, the event can appear extraordinarily bright. The alignment matters. A similar event occurring with the jet pointed elsewhere might look very different from our perspective. This is one reason some cosmic events are so rare. We may not simply need the event to happen. We need it to happen in the right direction. A gamma-ray burst can be brief. The initial flash may last seconds or minutes, but the event does not necessarily end immediately. After the gamma rays fade, an afterglow can remain. X-rays, ultraviolet light, visible light, infrared radiation. The afterglow can continue for hours, days, weeks, or longer depending on the event. Astronomers can follow the fading light. The burst becomes a story told in stages. First, an enormous flash, then a fading glow, then a quieter remnant, and eventually, the source returns to darkness. Some bursts are classified as long-duration gamma-ray bursts. These are often associated with the deaths of massive stars. Others are short-duration bursts. These are often associated with compact object mergers. The distinction is not perfect, but it provides an important clue. A few seconds of gamma rays can reveal the death of a star or the collision of stellar remnants billions of light years away. Imagine the energy involved. The original event may release more energy in a short time than a star like the Sun produces over an enormous span of its life. And yet the burst is temporary. A cosmic flash, a moment of extreme violence, then darkness. There is something strangely peaceful about that contrast. The universe can create enormous destruction without disturbing the quietness of space. There is no sound traveling through the vacuum, no thunder, no explosion that we could hear, only radiation moving outward. A burst occurs, light travels, space remains silent. Now imagine a gamma-ray burst occurring relatively close to the Milky Way. The consequences would depend on its distance and orientation. A sufficiently close burst aimed toward Earth could affect our atmosphere. Fortunately, dangerous nearby events appear to be extraordinarily uncommon. Most gamma-ray bursts occur at immense distances. They are cosmic events rather than immediate threats. Their greatest importance is scientific. They allow us to study the universe under extreme conditions. They also act as beacons. Because they can be detected from enormous distances, gamma-ray bursts can reveal distant galaxies that might otherwise be difficult to observe. A burst becomes a flashlight shining through the early universe. Its light passes through gas. Atoms absorb particular wavelengths. Those absorption patterns reveal the material between us and the burst. A single explosion can therefore become a probe of intergalactic space. The universe can destroy a star and, in the process, help us map the space between galaxies. This is a recurring theme. Violent events become scientific tools. Now let us move to something even stranger. A burst of radio waves lasting only milliseconds. A flash that appears in the radio sky and disappears almost immediately. These are fast radio bursts, or FRBs. They were first recognized as a distinct phenomenon in the early 21st century. They last incredibly short amounts of time, milliseconds, yet they can be detected across enormous cosmic distances. Their sources have been one of the major mysteries in modern astronomy. Some FRBs repeat. Others have been observed only once. Some originate in distant galaxies. At least some have been associated with magnetars. But the full population of FRBs may involve multiple types of sources or mechanisms. Imagine a telescope monitoring the sky. For hours, nothing unusual happens. Then, In less than the blink of an eye, a powerful radio signal appears. It is not a normal star. It is not a planet. It is not an ordinary radio transmitter. The signal sweeps across a range of radio frequencies. Then it vanishes. The telescope continues observing. Nothing. The event is over. A signal that traveled for millions or billions of years has passed through the universe and reached Earth for only a tiny fraction of a second. This is one of the most mysterious forms of cosmic communication. Not communication in the sense of an intentional message. There is no evidence that these signals are artificial. They are natural phenomena, but they feel almost like messages because of how brief and structured they can be. An FRB carries information about its journey. As the radio waves travel through plasma, different frequencies can arrive at slightly different times. This dispersion allows astronomers to estimate how much ionized material the signal passed through. The burst becomes a probe of the cosmic environment. It can tell us about the intergalactic medium. It can help measure the otherwise difficult to detect ordinary matter between galaxies. Again, a mysterious flash becomes a scientific instrument. Now imagine an FRB coming from a galaxy billions of light years away. The burst begins. Radio waves leave the source. They travel outward. They pass through the host galaxy. They cross intergalactic space. They encounter plasma. They continue toward the Milky Way. Eventually, they enter Earth's atmosphere. Radio telescopes detect them. The event is over. But astronomers can analyze the signal. They can estimate its distance. They can study its polarization. They can investigate its environment. They can compare it with other bursts. And slowly, the mystery becomes clearer. Some repeating FRBs have shown changes in activity. They can remain quiet for periods of time, then suddenly become active again. One source may produce multiple bursts over months or years. Another may flare repeatedly within a short observation. This suggests that at least some FRB sources are long-lived objects rather than one-time explosions. Magnetars are among the leading explanations for some of these bursts. A magnetar has an enormous magnetic field. Its crust can experience stress. Its magnetic environment can become unstable. A sudden release of energy may produce a radio burst. And sometimes, a magnetar in our own galaxy can produce an intense radio signal. In 2020, astronomers observed a powerful radio burst from a magnetar in the Milky Way. This was an important clue connecting at least some FRBs with magnetars. But the story is not necessarily complete. The universe may have more than one way to create an FRB. The same observable phenomenon may emerge from different physical processes. That is common in astronomy. Two objects can look similar from far away while being powered by different mechanisms. Now imagine an even shorter signal. A burst that lasts less than a millisecond. A cosmic flash so brief that it challenges the limits of detection. The shorter the event, the harder it becomes to observe. A telescope must be recording continuously. Its timing must be precise. Its data processing must be fast. Otherwise, the event can pass unnoticed. The universe may be producing rare signals every moment. We simply do not have detectors everywhere. We cannot monitor every wavelength. We cannot watch every point in the sky simultaneously. There may be entire populations of transient events that remain undiscovered. Future observatories may reveal them. New instruments are changing astronomy from a study of static objects into a study of a constantly changing sky. Instead of asking only, what objects are out there? Astronomers increasingly ask, what just happened? A star suddenly brightened. A black hole suddenly became active. A neutron star emitted a burst. A distant galaxy produced a transient. A gravitational wave passed through Earth. A radio signal appeared. The universe is alive with events. Now let us consider a peculiar type of star that suddenly becomes dramatically brighter. A nova. A nova occurs in a binary system containing a white dwarf and a companion star. Material from the companion can accumulate on the surface of the white dwarf. Hydrogen-rich gas builds up. Eventually, the temperature and pressure become sufficient for a thermonuclear runaway on the surface. The accumulated material is blasted outward. The system brightens dramatically, but unlike a typical supernova, the white dwarf can survive. The explosion is more like a surface eruption. The star remains. The process can potentially happen again. Some systems are known as recurrent novae because they have been observed undergoing repeated eruptions. These are rare. Imagine watching a seemingly ordinary star system. It sits quietly for years. Then suddenly, it brightens. It becomes visible to the naked eye from Earth under favorable conditions. People who have never noticed it before can suddenly see a new star-like point of light. Ancient observers sometimes described such appearances as new stars. The word nova comes from the Latin word for new. But the star was not actually born. It had simply become much brighter. The universe can make an old object appear new. Now imagine a recurrent nova. The eruption happens. The brightness fades. Years pass. Then another eruption. The system repeats its behavior. The white dwarf is accumulating material again. It is preparing for another event. Some recurrent novae are particularly important because the white dwarf may be gaining mass over time. If it approaches the conditions associated with a thermonuclear explosion, it could eventually produce a much more dramatic event. This makes recurrent novae objects of great interest. They are small laboratories of stellar evolution. Now move to an even more violent event. A supernova. The word is familiar, but the universe contains different kinds of supernovae. Some result from the collapse of massive stellar cores. Others arise from thermonuclear explosions involving white dwarfs. The details differ. The brightness can be enormous. For a brief period, a single exploding star can rival the brightness of its entire host galaxy. Imagine looking at a galaxy containing billions of stars. One of those stars dies. Suddenly, its light dominates the galaxy. A single object becomes the brightest point in an enormous stellar city. The explosion expands. The shock wave moves outward. Elements are created. Existing elements are scattered. The surrounding interstellar medium becomes enriched. Eventually, the visible light fades, but the remnants remain. A supernova remnant can persist for tens of thousands of years. The expanding shell interacts with surrounding gas. Shock waves accelerate particles. Magnetic fields become amplified. Cosmic rays can be produced. A beautiful nebula forms. The death of one star becomes a structure that survives long after the star itself has disappeared. One of the most famous examples is the Crab Nebula. It is the remnant of a supernova observed by astronomers in the year 1054. Chinese astronomers recorded a bright guest star that remained visible for an extended period. Today, the Crab Nebula contains an energetic pulsar at its center. The pulsar spins rapidly. It powers the surrounding nebula. Radiation and particles stream outward. The nebula glows. This means that a historical observation made almost 1,000 years ago is connected to an object we can study today. The past remains visible. Now imagine a supernova occurring in a galaxy far away. Its light reaches Earth. Astronomers detect it. They classify the explosion. They study its spectrum. They measure how its brightness changes over time. And if it belongs to a useful class of supernovae, it can help measure the expansion of the universe. Some supernovae have remarkably consistent intrinsic properties. Their apparent brightness can therefore reveal distance. By comparing distance with redshift, astronomers can study how the universe has expanded. An exploding star helped reveal that the expansion of the universe is accelerating. This was one of the most important discoveries in modern cosmology. A rare stellar death changed our understanding of the entire universe. The universe was not simply expanding. Its expansion was accelerating. Something was driving that acceleration. We call the unknown component responsible for the observed effect dark energy. We still do not fully understand what dark energy is. The word is a label for an observed cosmic phenomenon rather than a complete explanation. And so, a supernova leads us into one of the largest mysteries in cosmology. Dark energy. Most of the universe is not made of the ordinary matter that forms stars, planets, and people. Ordinary matter is only a small fraction of the cosmic energy budget. Dark matter contributes a larger fraction. Dark energy contributes even more. Yet we do not know its fundamental nature. Perhaps it is a property of space itself. Perhaps it reflects something deeper about gravity. Perhaps our cosmological model is incomplete. We know what the universe is doing. We are still trying to understand why. Now imagine the universe on its largest scales. Galaxies are moving apart. The expansion of space continues. Distant galaxies become increasingly separated. But locally, gravity can overcome cosmic expansion. The Milky Way and Andromeda are gravitationally bound. They will eventually interact. Their galaxies will merge over billions of years. The stars themselves are unlikely to collide directly because the distances between them are enormous. But their gravitational fields will interact. Their shapes will change. Their spiral structures may be disrupted. Gas clouds will collide. New stars may form. Eventually, the two galaxies may settle into a larger elliptical-like system. A merger is not a simple collision. It is a slow gravitational dance. It can take billions of years. And from a human perspective, almost nothing appears to happen. But over cosmic time, everything changes. Now imagine a galaxy merger happening much faster. Two galaxies with enormous amounts of gas approach one another. Their gravitational interaction compresses the gas. Star formation accelerates. The centers become active. The supermassive black holes may eventually spiral toward one another. Eventually, the black holes themselves may merge. Before that final merger, the system can produce gravitational waves. The galaxy becomes a laboratory for studying how galaxies and black holes grow together. Some of the most massive black holes in the universe may have grown through repeated mergers and accretion. A black hole is not always born massive. It can grow. It can consume gas. It can merge with other black holes. Over billions of years, small beginnings can become enormous. Now let us imagine a black hole merger from close to the event horizon. Of course, there is no ordinary vantage point from which we could safely watch. But mathematically, we can imagine the geometry. Two black holes orbit. Their horizons distort. The gravitational field becomes increasingly dynamic. The orbital frequency increases. The gravitational waves become stronger. Then the horizons merge. The final black hole rings down. Its distorted space-time settles into a stable state. The gravitational wave signal carries the signature of the entire process. The inspiral, the merger, the ring down. A detector on Earth can reconstruct these phases. It is astonishing. We can infer the properties of objects we cannot see directly. We can estimate their masses, their spins, their distance. We can even learn something about the final black hole, all from tiny distortions in space-time. And some mergers are rare because the black holes must find one another. Two isolated black holes can exist for billions of years without ever interacting. For a merger to occur, there must be a mechanism that brings them together. Perhaps they formed as a binary. Perhaps they became bound in a dense stellar cluster. Perhaps they were brought together by a galaxy merger. Perhaps a more complex dynamical interaction occurred. There are many possible pathways. The universe can create the same final event through different histories. Now consider a dense stellar cluster. Thousands or even millions of stars can be packed into a relatively compact region. The stars move rapidly. Gravitational interactions are frequent. Binary systems interact. Stars can exchange partners. Objects can be ejected. Black holes can sink toward the center. Neutron stars can interact. A cluster becomes a gravitational laboratory. Globular clusters are among the oldest stellar systems in the Milky Way. They contain ancient stars. They're stars formed early in the galaxy's history. They are like cosmic time capsules. Some contain unusual populations of compact objects. Millisecond pulsars are especially common in certain globular clusters. Why? Because dense stellar environments create opportunities for interactions. A neutron star can acquire a companion. Mass transfer can spin it up. The pulsar becomes a millisecond pulsar. The object may be ancient, but its rotation is incredibly fast. A stellar corpse has been rejuvenated through interaction. This is another beautiful example of cosmic recycling. A dead star can receive matter from a companion. The material transfers angular momentum. The neutron star spins faster. Its observational properties change. An ancient object appears newly energetic. The universe constantly reuses old material. Now imagine two stars passing close to one another inside a dense cluster. They do not necessarily collide, but their gravitational fields can exchange energy. One star may gain speed. Another may lose speed. Eventually, one can be ejected from the cluster. The cluster loses a member. A star becomes a runaway. Some runaway stars travel through the galaxy at enormous velocities. They may have been kicked out by interactions with binary systems, or they may have been accelerated by supernova explosions in binary systems. Imagine a massive star racing through interstellar space. Behind it is a trail of disturbed gas. It moves much faster than neighboring stars. The star is a cosmic runaway. It carries its own history with it. Perhaps its companion exploded. Perhaps another star kicked it away. The motion itself becomes evidence of an ancient event. Now imagine something even more extreme. A hypervelocity star. A star moving fast enough to escape the gravitational influence of the Milky Way. One possible mechanism involves interactions with the supermassive black hole at the center of our galaxy. A binary star system approaches the black hole. The gravitational interaction separates the binary. One star becomes tightly bound to the black hole. The other can be thrown outward at enormous speed. The ejected star becomes a hypervelocity star. It leaves the galactic center. It travels through the Milky Way. Eventually, it may escape the galaxy entirely. A star launched by a black hole. The black hole does not need to swallow the star. It can instead act as a gravitational slingshot. The star is accelerated away. Now imagine watching such a star move through the galaxy. It is not simply orbiting with the rest. It is traveling on a trajectory that may eventually carry it beyond the Milky Way. A star becomes an intergalactic traveler. Perhaps it began its life near the galactic center. Now it is moving toward the outskirts. Its journey may take millions of years, and its trajectory contains information about the gravitational potential of the galaxy. Again, an unusual object becomes a scientific tool. Now let us consider a star that moves so fast through a galaxy that its atmosphere interacts strongly with surrounding gas. A bow shock can form. The star plows through the interstellar medium. Gas accumulates in front. The material is compressed. The region glows at certain wavelengths. A stellar wind creates a bubble. The star leaves a trail. The object may look like a comet, even though it is a star. The shape is created by motion. A fast-moving star transforms the space around it. Nothing in the universe is truly isolated. Stars push material outward. Planets interact with stellar winds. Black holes launch jets. Galaxies heat gas. Supernovae send shock waves outward. Even empty space carries the consequences of these interactions. Now imagine a planetary system caught in a stellar explosion. A supernova occurs nearby. Radiation reaches the planets. A shock wave eventually arrives. The effects depend strongly on distance. A sufficiently distant supernova may simply become a spectacular astronomical event. A much closer one could alter the chemistry of a planet's atmosphere. It might expose the surface to increased radiation. It might leave traces of radioactive isotopes in geological material. Earth itself contains evidence of ancient nearby stellar explosions in the form of certain radioactive isotopes deposited in sediments. These clues can tell us that stars died relatively close to our solar system in the distant past. The galaxy is not static. Stars are born and die around us. The solar system has traveled through different regions of the Milky Way over its history. Perhaps it has passed through denser clouds. Perhaps nearby stars have exploded. The environment of Earth has changed, and yet life continued. Now imagine a star passing relatively close to the solar system. Its gravity can disturb distant cometary objects in the Oort cloud. The perturbation may send some comets inward. A star does not need to enter the planetary region to influence it. Gravity reaches far beyond the visible surface of a star. The galaxy is a gravitational environment. Stars interact even when they never touch. Now let us travel into the coldest regions of space. Some of the coldest natural environments known occur in interstellar clouds. Temperatures can approach only a few degrees above absolute zero. Molecules form. Dust grains become coated with ices. Complex chemistry occurs on microscopic surfaces. The space between stars is not empty. It can be a chemical laboratory. Hydrogen molecules, carbon monoxide, water ice, methanol, ammonia, organic molecules, all can exist in cold molecular clouds. Some of these clouds eventually collapse under gravity. Stars form. Planetary systems develop. The chemistry of the cloud can influence the chemistry of the resulting planets. The ingredients of future worlds may be assembled in darkness long before the worlds themselves exist. Imagine drifting inside a molecular cloud. The visible stars around you become obscured. Dust blocks the light. The environment is cold. The cloud is enormous. Yet inside, gravity is slowly working. Dense pockets form. They contract. Temperatures rise. Protostars appear. The cloud begins producing stars. A dark cloud becomes a stellar nursery. Darkness becomes creation. This is one of the most beautiful transformations in astronomy. Now imagine an exceptionally massive protostar. It gathers material rapidly. Its gravity pulls in gas. A disk forms. Jets emerge. The star grows. Eventually, nuclear fusion begins. A new massive star enters the main sequence. Its lifetime will be short compared with the Sun's, but its influence will be enormous. It will emit intense ultraviolet radiation. It will shape the surrounding cloud. Its winds will blow bubbles. Eventually, it may explode. The cycle begins again. Birth, life, death, recycling. Now consider a very rare possibility in stellar evolution. A star that appears to have survived a supernova. In some binary systems, one star can explode while its companion survives. The explosion can dramatically alter the orbit. The surviving star can receive a kick. It may become a runaway. The compact remnant remains nearby. Two objects that were once a binary may now be traveling together through space. The system carries the scars of the explosion. Astronomers can study the motion of the surviving star and infer what happened. Sometimes the surviving star may eventually interact with the compact remnant again. The system's story continues. Now imagine an even stranger event. A star and a black hole in a close binary. The star loses mass. The black hole gains it. An accretion disk forms. Jets may appear. The system becomes an X-ray binary. Some X-ray binaries are transient. They remain quiet for long periods. Then suddenly, the accretion rate increases. The system brightens dramatically in X-rays. The outburst can last weeks or months. Then the system fades again. The black hole has awakened. This behavior can repeat. A dormant system becomes a powerful X-ray source, then returns to silence. The universe contains sleeping giants, and sometimes something feeds them. Now imagine an X-ray binary containing a neutron star. The neutron star's magnetic field can channel material toward its magnetic poles. Hotspots form. The system emits X-rays. As the neutron star rotates, the emission may vary. The result can be pulsating X-rays. A rotating compact object becomes a beacon. Again, a lighthouse. But this lighthouse is powered by matter falling into a neutron star's gravitational field. The material does not simply land on the surface gently. It accelerates. It becomes extremely hot. It releases energy. The compact star glows in X-rays. Now consider a neutron star with a crust that suddenly rearranges. A burst occurs, then another. Some sources produce repeated short X-ray bursts. Thermonuclear burning can occur on the surface when material from a companion accumulates. Hydrogen and helium ignite. The neutron star experiences a nuclear flash. The event can last seconds. The star returns to its previous state. Then material accumulates again. Another burst may occur. These thermonuclear X-ray bursts are another example of a compact object turning ordinary matter into an extreme event. The universe can transform a thin layer of accreted material into a flash of X-rays. And all of this happens on a star only a few tens of kilometers across. Scale becomes almost meaningless. A tiny surface can host extraordinary energy releases. Now, somewhere far away, another neutron star may be spinning silently. Its beam sweeps through space. Perhaps it is pointed away from Earth. If so, we may never know it exists. This is another form of astronomical selection. The universe can contain an enormous population of objects that are invisible to us because their radiation does not point our way. Pulsars are especially affected by geometry. A pulsar can emit beams from its magnetic poles. If the beam crosses Earth, we detect pulses. If it misses Earth, the object may be much harder to identify. So the number of pulsars we see is not necessarily the number that exists. There may be many more hidden. The same principle applies to jets, to gravitational lensing, to transiting planets, to eclipsing binaries. Observation depends on geometry. The universe is three-dimensional. We see only one particular line of sight. That limitation creates mysteries. Now imagine a planet orbiting a star with two suns. Binary stars can host planets. A world may orbit both stars together, tracing a path around the pair. From the surface, there would be two suns. Their positions would change. Their shadows would overlap. Sunsets could become complicated, but the physics remains possible. Some circumbinary planets have been discovered. They are not the most common worlds we know, but they demonstrate that planets can form in environments more complicated than our solar system. Now imagine a planet orbiting one star while another star passes relatively nearby. The second star's gravity can disturb the planet's orbit. Planetary systems can evolve through gravitational encounters. A world may move inward. Another may move outward. A planet can be ejected. A moon can be captured. Orbits can change. The architecture of a planetary system is not always permanent. The early solar system itself was likely much more chaotic than it appears today. Giant planets migrated. Small bodies were scattered. Moons formed. Collisions occurred. The calm arrangement we see now may be the result of billions of years of gravitational evolution. Now imagine a planetary system where a giant planet has migrated extremely close to its star. A hot Jupiter. Its orbit may last only a few days. The planet is huge. The star dominates its sky. The atmosphere is heated. Strong winds can carry energy around the planet. Some hot Jupiters may have temperatures high enough for unusual chemistry. Certain elements can condense on the night side and evaporate again on the day side. Some planets may even have winds carrying vaporized metals. The universe creates weather systems that sound impossible until physics explains them. Now imagine an ultra-hot Jupiter. The dayside temperature can reach thousands of degrees. Molecules may be broken apart. Atoms become dominant. The planet is not merely warm. It is exposed to conditions resembling those of a cool star more than a familiar planet. And yet it remains a planet. A world can exist under conditions completely unlike Earth. This diversity is one of the great discoveries of exoplanet science. Our solar system is not necessarily typical. It is simply the system we happen to live in. Now imagine a planet with a deeply inflated atmosphere. The intense radiation from its star heats the upper atmosphere. The gas expands. The planet's apparent radius becomes larger than expected. Some hot planets are losing atmospheric material into space. Hydrogen can escape. Other gases may escape depending on temperature and gravitational strength. A planet can slowly evaporate. Given enough time, the world may lose much of its atmosphere. The final remnant could be very different from the planet that formed billions of years earlier. Now imagine a small rocky planet orbiting extremely close to its star. Its surface is bombarded with radiation. Its atmosphere is stripped. Its rocks may heat dramatically. The planet may become barren. Perhaps it began with oceans. Perhaps it once had an atmosphere. But the star gradually removed its protection. Planetary evolution can be a story of loss. Not every world remains habitable. Some become frozen. Some become scorched. Some are stripped. Some are destroyed. And some remain stable for billions of years. The universe contains all of these possibilities. Now let us slowly pull away. The hot planets become tiny. The neutron stars become points. The black holes become shadows. The galaxies become distant islands. The cosmic voids surround everything. And once again, the darkness becomes enormous. Somewhere, an FRB has just flashed. Somewhere else, a gamma ray burst has begun. A white dwarf is accumulating matter. A magnetar is quietly rotating. A black hole is feeding. A supernova remnant is expanding. A rogue planet is drifting. A distant galaxy is forming stars. A gravitational wave is traveling through space. All of these events can happen simultaneously. The universe has no single storyline. It is a collection of countless stories unfolding at different speeds. Some end quickly, some last billions of years. Some are so slow that an entire civilization could disappear before the event noticeably changes. And some are so fast that if our telescopes are not looking at precisely the right moment, we miss them completely. This is why the rarest things are so difficult to find. They require patience, sensitive instruments, wide surveys, good timing, and sometimes luck. A telescope can spend years watching the sky. Then, one night, something happens. A flash, a burst, a new point of light, a sudden disappearance, a strange spectrum, a tiny movement, and an entirely new mystery begins. Perhaps the object has been there for billions of years. We simply noticed it for the first time. Perhaps the event lasted only seconds. Perhaps the signal had been traveling for billions of years before reaching us. Astronomy is filled with these delayed encounters. The universe does not bring events to us directly. It sends us messengers, light, particles, gravity. We receive whatever survives the journey. And sometimes, the message is extraordinarily old. The light from a distant galaxy may have begun its journey before Earth existed. A gravitational wave may have originated before humans appeared. A neutrino may have escaped from a stellar explosion millions of years ago. We are surrounded by ancient information. Every clear night is a view into cosmic history. Even the light from the moon is already slightly old by the time we see it. The sunlight we receive began its final journey from the sun about 8 minutes earlier. The sunlight from distant stars can be years, centuries, or thousands of years old. The farther we look, the older the light becomes. And when we observe the earliest galaxies, we are looking back billions of years. The universe is constantly sending us memories. Some memories are bright, some are faint, some are only radio signals, some are particles, some are ripples in space-time, but all are pieces of the same enormous story. And perhaps now, as you listen, you can imagine drifting along with one of those photons, leaving a distant galaxy, passing through empty space, crossing enormous cosmic voids, moving silently between galaxies, never stopping, never becoming tired, just traveling. Eventually, after billions of years, reaching a small planet around an ordinary star. A telescope collects it. A screen lights up. Someone looks. And for one brief moment, the distant universe becomes visible. That is the journey of light. And that journey continues. There are still many rare things ahead. Stranger forms of matter. Ancient cosmic relics. Impossible-looking objects. Rare planetary systems. Mysterious remnants. And events so unusual that scientists sometimes debate exactly what they are seeing. The universe is not finished revealing itself, and neither are we finished exploring it. For now, though, allow the cosmic flashes to fade. The gamma rays disappear. The radio bursts become quiet. The supernovae dim. The X-ray binaries settle. The black holes become silent. The distant galaxies continue drifting, and the night becomes peaceful again. You are floating through an ocean of darkness. There is no wind, no sound, no urgency, only distant light. The universe continues its ancient motion. Stars are born. Stars die. Black holes grow. Planets orbit. Galaxies merge. Space expands. And through it all, tiny signals travel patiently toward distant worlds. Perhaps one of them is traveling toward us right now. Perhaps billions of years from now, someone will detect it. Perhaps it has already passed us without being noticed. Either way, the universe keeps sending its messages. Quietly, patiently, across distances too large to imagine. And as you rest here, we can continue drifting toward the next region of the cosmic unknown. Because beyond the transient flashes and violent explosions are even stranger possibilities. Objects with bizarre compositions, worlds with unusual atmospheres, stars with extraordinary chemistry, ancient remnants from the earliest universe, and perhaps some things that exist only because the laws of physics permit them under conditions almost never found in nature. The darkness ahead is still enormous, and somewhere within it, something rare is waiting to be discovered. For now, though, let everything become quiet. The stars can shine without you watching. The galaxies can drift without you following. The black holes can spin without you understanding them. You can simply rest. The universe is very old. It has been here for billions of years. It has survived countless stellar deaths, countless collisions, countless transformations, and it will continue long after tonight has passed. So let your thoughts become still. Imagine the distant glow of a galaxy slowly fading. Imagine a lone photon crossing the darkness. Imagine a neutron-star turning silently in the distance. Imagine a planet orbiting its star beneath an unfamiliar sky. And imagine the enormous space between everything. Quiet, dark, endless. For a moment, there is nothing to do, nothing to chase, nothing to solve, only the slow journey through the universe. And the next part is waiting beyond the darkness. We have traveled through enormous galaxies and tiny stellar remnants. We have watched stars collapse. We have passed close to black holes. We have followed gravitational waves. We have listened to brief radio flashes arriving from billions of light years away. We have imagined rogue planets drifting alone through the darkness, ancient stars shining from the earliest chapters of cosmic history, galaxies almost completely hidden from view, and violent explosions that appear for only a moment before disappearing again. But there is something important we have slowly discovered along the way. Rarity in the universe does not always mean something is small. It does not always mean something is powerful. It does not even mean something is completely unique. Sometimes something is rare because it requires an extraordinary coincidence. Sometimes it is rare because it exists only briefly. Sometimes it is rare because it formed under conditions that almost never occur. And sometimes it is rare simply because the universe is so enormous that even an event happening frequently can appear incredibly uncommon from our small corner of space. Tonight, we will move deeper into that idea. We will leave behind the objects we already know and travel toward the final collection of cosmic curiosities. Some are strange remnants. Some are unusual stars. Some are rare planetary environments. Some are almost impossible alignments. And some are mysteries that may not yet have complete explanations. So allow yourself to settle down. Let the room around you become quiet. Let the sounds of the night become distant. And imagine that the earth beneath you is slowly becoming smaller. The oceans disappear into a blue curve. The continents become indistinguishable. Clouds become delicate white patterns. The atmosphere becomes a thin glowing shell. The moon moves farther away. The sun becomes another bright point. And then even the sun becomes small. You are drifting outward, past the planets, past the asteroid belt, past the distant icy bodies, and into interstellar space. Here, the solar system is only a tiny island. The darkness stretches in every direction, and somewhere ahead, a rare object is waiting. Imagine a star that contains almost no elements heavier than helium. It was born from material that had been only minimally enriched by earlier generations of stars. Its chemistry is ancient. Such stars are extremely valuable because they preserve information about the early universe. The universe began mostly with hydrogen and helium. The heavier elements were created later inside stars and during explosive events. So when astronomers discover a star with an extraordinarily primitive chemical composition, they are effectively finding a piece of cosmic archaeology. The star may have formed billions of years ago. It has survived all this time. Its light reaches us now. Its atmosphere contains clues about the environment in which it was born. A few atoms in its spectrum can tell us about ancient stellar explosions. A tiny amount of iron, a little carbon, traces of other elements. The chemical pattern becomes a fossil record. The star itself may look ordinary, but its chemistry can be extraordinarily rare. Imagine looking at its spectrum, a long line of colors, small dark absorption lines. Each line corresponds to an element: hydrogen, calcium, iron, carbon, magnesium. Perhaps an unusual abundance pattern appears. The astronomer begins to reconstruct the star's history. Maybe the gas from which it formed was enriched by only one or two earlier supernovae. Maybe it formed in an early dwarf galaxy that was later absorbed by the Milky Way. Maybe it is one of the oldest stars still shining. The universe has preserved a witness from its youth. Now imagine another kind of stellar rarity, a star that is almost entirely composed of helium, a stripped star. Perhaps its outer layers were removed by a companion. Perhaps stellar winds stripped away material. Perhaps a previous interaction exposed deeper layers. The star's appearance no longer resembles an ordinary star like the Sun. Its history is written in its atmosphere. Stars are not isolated objects with simple lives. Binary companions can change them. A star can lose mass. A star can gain mass. A star can exchange material. A star can merge. A star can be thrown from its original environment. Its final appearance may tell us little about its beginning unless we understand the interactions that shaped it. This is why rare stars are so valuable. They reveal unusual evolutionary pathways. Now imagine two stars orbiting each other so closely that their outer atmospheres touch. They share material. They may eventually merge. A contact binary. And tonight, perhaps you have been traveling through that dream. From the smallest flashes to the largest structures. From ancient stars to future worlds. From black holes to cosmic voids. From violent explosions to silent planets. 100 rare and extraordinary possibilities, all scattered across an incomprehensibly large universe. And yet, after all that distance, we return to the same place. A quiet room, a quiet night, a human mind, and perhaps a little more wonder than when we began. So let the final stars fade now. Let the galaxies become softer. Let the cosmic web disappear into darkness. Let the distant black holes become invisible. Let the last photon continue on its journey. You do not have to follow it. You can simply rest. The universe will keep traveling. Time will keep passing. Stars will keep being born. Stars will keep dying. And somewhere beyond everything we can see, the next rare thing is already happening. We just haven't discovered it yet. Good night. Sleep peacefully. And remember that above the quiet world beneath you, an unimaginably vast universe continues its slow and beautiful journey through the darkness.